In this session, we're going to build off our last session of parameterized classes by adding parameterized methods inside of these parameterized classes. Parameterized methods work along with a parameterized class to create solutions that you may need. So in this session, we're going to expound on parameterized methods to derive at these solutions. So let's start off with box in our file box.scala, which we created. So here we are in case class box T with the primary constructor, with the T bringing in a T. Now let's say we want to create a method inside of this class called CoupleWith. And CoupleWith is going to take another parameterized type as we bring in as a method parameter type U. Again, T and U can be anything. And the return type of this is going to be a box of a couple of T and U. So what's the whole idea for this method? We have T, it's already established. We're calling CoupleWith, that's going to bring in a U, and what I'd like to do is return a box with a couple of both T and U. So now we're getting to a place where we see parameterized types everywhere. And you'll probably realize that this video series is now getting a little bit more complicated. But don't panic, let's take this piece by piece. First, again, CoupleWith takes a parameterized type U. We do that because U is not declared at the class level. It is only used at the method level. So we choose not to declare it at the class level because it's really not needed there. We're only using it at one place, and that's the method. Again, a parameterized type can be anything. Therefore, U can be anything. This is going to return a box of type couple, which couple has types of their own. That will contain T, type established when we created the object, and type U, the type we are providing in the method parameter. And remember, the reason we're doing this right over here is that couple has two parameterized types, one for the first item and the other one for the second. So let's finish off our implementation. Obviously, this is a method and it's not abstract. It's not part of an abstract class. And what I'd like to return is new box with a new couple with T and U. Let's add the final brace here. But we can clean this up. Remember, box and couple are case classes. So we can get rid of the new keyword here, and we can get rid of the new keyword here. So let's compile box.scala. Everything works. We know that we are on the right track. Now, let's put this into a script. So let's go back to our code, and let's open up our box script that we created in our last session. So in this box script, I'd like to create the following. Let's say we want to create int box4, and we're going to create a box here with the number 200. And let's say for our example that I would like to return a couple int string box. And what we're going to do is we're going to take this int box of 4 and we're going to call CoupleWith. And we're going to couple this with Scala. What is this going to return? Well, this is going to return a box with a couple with int and string. And if you plug this into a REPL, you'll find out that this indeed does return that particular type. And because it returns this type, we can do the following. Because remember, at the outer shell, we have a box. How do we get the internals of a box? We'll call T. Then we have a couple. How do we get the first and second element from the couple? We can call either first or second. We can run in our script and see what the result is. Parameterized types working in conjunction with parameterized classes. And I think you may start seeing the beginning of the beauty of immutability in functional language like Scala and how all this works. So let's save this and then let's run our script. This is called box script. Here's the number and here's the string, our int and our string. Now let's try something else special. Let's say that in our couple class we want to create a method called swap. And swap will take the first element and make it the second, and will take the second element and make it the first. Question is, do we need parameterized types in our method? So let's go to our code. This time, I want to take a look at couple. Given this, I want to create a method called swap. Do I need parameterized types here? And I just put question marks as placeholders. Do I need parameterized types here? The answer is no, because they've already been defined up here. We're using the same types. We're using the same A and the same B. Therefore, we do not need parameterized types here. And I included this in this session just to show you that if they are already declared as a type, you don't need to declare them elsewhere. What's going to be the implementation for this? Well, we'll just return a new couple where we will provide it the second and the first. But what is interesting about this is if I want to be explicit about it, is I could state that the couple, or what's going to be returned here, is a couple of type B and A. In other words, these are going to be switched because this is a swap. Whatever the type B is going to be in the first placement. Let me highlight that. And A is going to be here in the second placement because we're returning a couple of second and first. And this is a new instance. Remember, we embrace immutability. So let's compile this for a sanity check. There it is. Now let's create some code in our couple script and try our swap. And this time I'd like to create a couple more employees. Let's head over to our code. And this time I want to edit our couple script. Here it is. And as stated previously, I'm going to create an employee couple. And this is a couple of a new employee. And let's do the Lisp founder, John McCarthy. And how about Python? All right, so we have a couple with 2 employees. So let's print out and let's see what happens, just to make sure we're doing okay. And let's see what it looks like when we do a swap. Remember, swap is a method now, and it's part of couple. So let's make sure this is compiled once again, and now we will run our script. First one, we had John McCarthy, and we had the employee Guido van Rossum, programmer, and since we called it with swap, here it is. Guido is first, John is second. So parameterized methods can be used in conjunction with parameterized classes. If a type is already known at the class level, it does not need to be declared at the method level. And this only brushes the surface of types in type system. There's a whole new world out there when it comes to type systems. In this session, we will cover objects. So we all know that objects are instantiated from classes. In Scala, there's a way that you can create an object without a class, and it uses the object keyword. So let's go to REPL and show off an object. So here we are at the REPL, and I'm going to do the following. And that's it. This is an object. No class, just straight to the object. Because you can only have one object with no class, that means that this is a singleton. A singleton was first named in this seminal book. Design Patterns, Elements of Reusable Object-Oriented Software. This is also known as the Gang of Four book. For a more modern version, there's Head First Design Patterns. The original Gang of Four book uses C++. Head First Design Patterns uses Java. Both are excellent books, and both are on O'Reilly's Safari. Now, the singleton pattern is defined in both books as ensure a class only has one instance and provide a global point of access to it. So that's what a Scala object does. And let's prove it. Let's go back to the REPL. All right, so here we are back at the REPL. I'm going to do val a is equal to my object. And we're able to make an assignment. Val a is being pointed to my object. I'll do val b pointing to my object. That works out great. Now let's prove further that this is a singleton. It should stand to reason that both a and b are equal. That is true. And it should also stand to reason that a is pointing to the same thing as b. That is also true. Since they are both equal and both pointing to the same reference, it is a singleton. There is only one object, and I have global access to it. So what do we do with this object? Well, let's create a script that will do just that. In the past, I created a class in its own file. So in our example, what we're going to do is we are going to just create a script. Since we've already had some practice with compiling, let's just keep it simple, everything inside of a script. And this script is going to be called objectscript.scala. Okay, and here we are in our editor. I've created a file called objectscript.scala, and I'm going to get started. So I'm going to do the same thing again. I'm going to create my singleton within here called my object, and I'm going to put a method in here. Now I'm going to output the result. Let's go ahead and save this and run the script. So here I am at the command line and running my script. There it is. We obviously get 15. So let's go back to our code. So I'm calling foo with 2 ints. I'm calling it with 5 and 10. Obviously, that's going to be 15. But really, that wasn't the point for this. So let's take a look at this again. My point is, how are we calling it? myObject.foo. It looks like a static method in Java or a class method in Ruby or Python. But we don't have static methods or class methods in Scala. We have object methods, methods that belong to the object. They look the same, we use them the same, they feel the same, but by definition, they are different, since they are not methods tied to a class like they are in Java, Ruby, or Python. They are methods tied to an object. Again, an object is just like an object as if you had created it with a new keyword. but it's pre-instantiated and there's only one. And this is what we use for what was once considered static calls. We don't have a static keyword in Scala. Inside of the object, you can have vars, vals, or defs. We have a def in our example here. We'll play around with some more in the next session. Now, some other rules. You cannot extend from an object. In other words, I can't have a class called class foo extends my object because my object is already an instance. But you can have an object extend from a class with some interesting results. So let's try out that neat little trick. Let's say we create an employee class just like we did in chapter 5, but we'll recreate it here and not bring in the rest of the baggage. So just like before, class employee, we're bringing in a first name, a last name, and a title. So what can we do with this? Well, let's extend the object from the class. Very interesting. I'm taking an object and I'm extending it from a class. So what can we do with this? Well, let's try out some print lines. This is really the same thing as an instantiation. Object new extends employee. Probably a little bit more esoteric for an introductory video series, but I thought it was interesting. So let's go ahead and save this, and let me go ahead and run this script at the command line. Donald Knuth, programmer. Now, when do you use objects as opposed to classes? Well, in classes, if you need to define a template to create multiple instances, definitely you need a class. And if you need every instance in charge of its own state, definitely you need your own class as well. But for objects, if you need a singleton, if you need a factory pattern being creating families of related or dependent objects without specifying or hiding their concrete classes, if you need that sort of pattern, and we'll make use of this factory pattern in the next session, if you need this factory pattern, then you would use an object. If you need to implement pattern matching logic, if you need a utility method, one that does not require an instance or a state, then you'll use an object. If you need to set up some kind of default values, then you'll need an object. And if you need a main method, you'll need an object. So let's go on that particular thread, and let's talk about the main method. Nearly every static type language has the notion of a main method. C has one, C++ has one, Haskell has one, Java has one, and of course, Scala will have one too. A main method is an entry point to a program. In other words, where the program starts. Since Scala is a JVM language and a static type language, let's first take a look at what a main method in Java looks like. So here's Java's main method. Public class runner, public static void main string args, and I have a system out print line. So let's work off of this and let's create our own runner class. And you can't see my fingers, but I'm doing the quotation mark sign language when I discuss class. Because we're not going to create a class for our example, we're going to create an object. So I'm going to create a file called runner.scala, and we'll compare it with this slide a bit at a time. Let's get started. Okay, so here we are. I have runner.scala, and I'm going to create a method, and I'm going to make it look very much like the Java equivalent. So let's go back to the slide. Public class runner, and the main method is public static void main string and args. So this method is called main. We know that. It needs to be public, but everything is already public in Scala, so we don't need to declare anything in Scala as such. It needs to be static, so we have public. Again, we don't need that. We have static. We don't have static, we have objects. So that means that runner can't be a class, it's going to be an object. We have void, but we already know what void is. It's unit. So this method needs to return unit. Next, obviously it's the main method, that's the name of the method. And we have an array of strings. Now we haven't discussed arrays yet, but arrays are a collection, and in this case this is going to be a collection of strings. And as far as args is concerned, well, that could be whatever we want to call it. It could be args, argv, or arguments. Doesn't matter. So we have all the information we need, so let's create our runner. So object runner, remember the class before was called runner in Java, but since the main method has to be static, we're going to put this inside of an object. The method is called main. The method parameter was called args, but we could call that argv, arguments, or whatever we want to call it. But it was an array of string. And this returned a unit. There's no need for a public. Everything by default is public. And here's our implementation. So let's compare and contrast once again. Here's the Java version, and here's the Scala version. So let's compile this. Remember, we have to compile this and then run it. Remember, we aren't running a script in this example. We're compiling and running the object at the command line, and it works. Can we run it with Java? So in other words, can we say Java space runner? Answer is yes, with something else along with it. And we need to tell Java that there is an extra jar that we need, scala-library.jar. When you download Scala, you expanded an entire package for Scala. If you used an installer, you may have to look for that Scala folder where it was installed. In there is a lib directory, and there's some jar files. And within that lib directory, there's a jar file called scala-library.jar. So if I were to run this with Java, I would have to make sure that I have everything correct. First, -cp stating where the class path is. In other words, where all my classes are located. Well, I have classes here already. I have runner class, runner $.class. So all my class files are here. So if I were to do this, I would do java-cp, make this directory that I'm in part of my class path. And I have my Scala installation in my home directory. And I'm using the latest version, Scala 2.11.7. And in my lib directory, wherever my Scala is installed, I'm going to include scala-library.jar, then call runner. And there it is. So I'm able to call this either using Scala or Java. Now, if you are using Windows, let's go over to this slide and show you that. So here's an example Windows Java call if you were to run a Scala program. If you did use the installer, this will probably look 100% as to what you're trying to do. Java space -cp dot semicolon, that's the way it's done in Windows. And because I have a space in program files and x86, I'm putting the whole thing inside of a quotation mark and then calling it with runner. Next, you could also create a runner without a main declaration. And all we have to do is just extend scala.app. So let's create another file called runner app. And let's give that a try. So here's runner app. I'm going to create an object, and this will extend app. And here what I'll do is say println hello Scala edition. Simpler than the previous example. And that's it. No need to declare a main method. Now let's compile and try it. Wonderful. That works really well. So when would you use a script versus an object with a main method or extending app? My opinion is if it's utilitarian or a quick hack, something that's going to perform some kind of work for you, keep it as a script. But if it's for production and you need the performance out of it, compile it and use an object with a main method. So in conclusion, objects are singletons. Objects are Scala's replacement for static. Objects are typically meant for factories, utilities, defining pattern matching, defining defaults, and for creating main methods. Main methods are inside of objects, always. And that's because objects represent what used to be represented as static in Java. You can forego the main method declaration and have your object extend scala.app. In this next session, we discuss companion objects. In our last session, we described objects as singletons. Companion objects are still singletons, but they service a class, an abstract class, or a trait, which we won't be able to cover in this video series, but just think of a trait as a structure that has nothing but abstract methods. The rule for a companion object is the object name has to be the same name as the class that it supports. The object and the class also have to be in the same file. What are some of the benefits of a companion class? For one, they can share each other's private information. If the object has private information, the class can have access to it. If the class has private information, the object has access to it. Because of this relationship, the companion object is in a unique position to create instances of a class it supports and perform operations that other objects can't because of this close relationship. So let's try 3 scenarios in this session. One where the object has private information for the class, one where the class has private information to the object, and finally let's create a real-world example for our employee class. First example, object has information for the class to use. This is an example I wrote for the Scala Cohen's project a few years ago. Some of the examples there are also in this video series, and you can find out more about the Scala Cohen's project at scalacohens.org. Back to our code. We will have a secret agent class and companion object. The companion object will hold the bullets used by the secret agents, but the bullets are private since we don't want others knowing how many we have. And the class can have access to them. So let's create a file called secretagent.scala. All right, so here we are with secretagent.scala. In here, I'm going to create a class called secretagent, and this secret agent is going to have a name, we'll get started with that. And now I'm going to create a companion object. So this has to have the same name, and it's in the same file. So this is a companion object. Now within here, this is going to be encapsulated. So let's say that we have private var b, and this is the number of bullets that we have. And this is going to be capped at around 3,000. So the agency has about 3,000 bullets, and this is available privately. So we're going to have this def here that if we call decrement bullets with a count, and let's say for this example, if the count coming in, the subtraction from B is going to be less than or equal to 0, we'll just say that the number of bullets now is 0. Otherwise, let us take the bullets and decrement by that count. Finally, I suppose we can make this protected, but for now, let's just say that for bullets, we just want to return the number of bullets. So far, so good, but we need to come back up here because shoot does not exist for our particular class. So let's say def shoot, and here are the number of bullets. This will return unit, and what we're going to do is we're going to call decrement bullets with the number of bullets that we want to shoot. Now, we could clean this up a little bit using imports. And one of the things we could do is we could do the following. We could say import secret agent dot underscore. And this is going to mean that every method that is inside of the secret agent companion object is imported. Now, we could just get rid of this and just make it look like there's a method called decrement bullets, just for aesthetic purposes only. So this shows that bullets are limited. Rough times at the agency, we have to keep track of all those agents firing bullets. The only objects that have access to the stash are the secret agents themselves. Now, let's create an object that will run our file, and we'll call this one secret agent runner. Why a different one? Well, a companion object cannot have a main method. So therefore, the secret agent object is out of the question. So let's create one called secret agent runner. And this will extend app, and we'll have a few secret agents set up. So the first one, let's set up James Bond. Next one, his American counterpart, Felix Leitner. And let's make him Jason Bourne. Next one will be Agent 99. And finally, let's have Max Smart. All right, so we have 5 agents. Now, each of these agents are going to share their share of bullets. So for Bond, let's say he will shoot 800 of them. Let's say Felix will shoot 200. Jason will shoot 150. 99 will shoot 150. And Max will shoot 200. So after all this, let's do a print line here. And we want to ask the question, how many bullets were used up by all our agents? So we've created some agents, Bond, Felix, Jason, 99, and Max. They're all shooting their share of bullets. And then finally, we're going to ask the question, how many bullets are left? Everything looks in order. So let's go ahead and save it. And then let's go to our command line, compile it, and run secret agent runner. The bullets are shared among the secret agent. And that's one benefit of companion objects, and it works. In the next example, we discuss our next benefit, that benefit being that the companion object having access to the class object's secret information. We're going to create a class called superheroes, and the object is going to have access to the private information in the class. So we're going to start off with superheroes.scala, and we're going to try out the following. So let's go over to our editor. Okay, so here we are under superheroes.scala. And what I'd like to do is create a class. So here we are, class person. And this isn't going to be the same person that we've created up to this point. Let's call it superhero name string. All right, so notice right here that we have a superhero. And the superhero name is going to be private. So no one has access to this except for the companion object. Companion object is going to have a method called show me inner secret. This will take in a person and it will reveal a secret identity. Let's go ahead and save that. And now let's create a runner to run our code. Remember, it has to be different than the companion object because the companion object cannot have a main method nor could it extend app. We'll call this one superhero runner extends app. Now, Val, so let's create Clark. This is a new person named Clark Kent, and his secret identity is Superman. So how about this? Print line. And what I'd like to do here is call the companion object and ask the companion object, show me the inner secret for Clark Kent. So we go ahead and save this, superheroes.scala, and let's run it on our command line. But first, compile. So here we go. There it is. And now let's run superhero runner. There it is. There's Superman. So there goes Superman's identity. We see the purpose for companion objects. Let's go back to the code and how they're different from regular objects. So this companion object was able to display the secret identity for Clark Kent, which was Superman. So let's do something down to earth. Let's bring back our employee example, but this time we want to have an employee have an automatic hire date, and that would be today's date when they're hired. But we also want to make it testable. So let's create a file called employee-design.scala, and we'll recreate the employee class file, but this time we want to add a hire date. And this will only work with an underlying Java 8 JVM, since Java 8 has a datetime API that's exceptional, and it came with that release. Okay, so here we are under employee-design.scala, and what I'd like to do is I'd like to import Java time, because this is the datetime API that I'd like to use, and I'm going to create a class called employee, which is similar to the ones we've been creating for the last few sessions. This will have a first name, this will also have a last name, and this will also have a title. But what's new is we're going to have a hire date. When was this employee hired? But now we have a problem. We want to have the ability to create an employee where the hire date is automatically set to today's date. What are our choices? Well, we can use default parameters. We can also create an alternate constructor or an ancillary constructor. The problem is that while that will work, it is very difficult to create a consistent scenario where we can test the code. It's called a code smell because inside of a constructor, we have something that is unstable or inconsistent. Again, every time we're going to create this code, it's going to use a different date, which is fine for what we want, but as far as testing, it's not consistent because time always changes. So what other choices do we have? Well, we can use the object to create instances for us. Remember, one of the key reasons for the object's existence is to be a location for factories. So let's create some factories. So within here, I'm going to have a method called create, and from here, I'm going to return title and finally the local date. So what is this saying right here? Well, we have a method called create, and if you give me the first name, the last name, and the title for the individual, what we're going to return is a new employee with the first name, the last name, the title, and within here, inside the factory, this is a really good place to put it, give me the latest local date. Now, if you're unfamiliar with the Java 8 datetime API, this says give me the date. The date means no time zone, no time, just give me the date itself. And this is our factory. Again, the local date is not an instantiation inside of a constructor. This is part of a method which is inside of an object. Therefore, it is not a code smell because we're not instantiating or creating anything new inside of a constructor. So let's make a runner to try out our factory. And within here, let's choose another programmer, and we'll try the famous Ken Thompson. And what I'd like to see is the hire date. All right, there we go. So we're using a factory, in this case, to create our employee, just by only giving it the first name, the last name, and the title. And then finally getting the hire date in return. So we went ahead and saved this. Let's compile employee-design.scala, then run the employee design runner. So here we are in our command line. That looks great and wonderful. Now, one of the things we can do is design our code to where everything is locked up, and as far as direct instantiation, we lock everything up and say that employees will always be created by our factories. So let's do that. Let's go back to our code. So what I'd like to do here is for the primary constructor, let's make that private, and let's have two different factories. And this one will contain the local date. What is going to be returned? Well, this employee with the first name, the last name, the title, and the hire date. So no more direct instantiation. We've made the entire primary constructor private. Now this is a great design. The companion object has access to the private constructor. Again, even though this is private, since this is the companion object, we have access to it. Because objects have access to any of the class's private information. Now, I would be of the opinion that the primary constructor for the employee class be protected instead. That way it could be accessed by a test. Protected being anything within the same package. Now, this code is going to work whether this is private or protected. Again, the reason I like it for it to be protected is so that I have access to test it. Protected means anything that is within the same package can have access to it, and any subclass can have access to it. Therefore, if a test is in the same package, then that test has the ability to directly access production code. So let's go ahead and save this, and let's give it a try. Great. It all works magnificently. And those are companion objects. So, in conclusion, companion objects have the same name as the class that they work for. Companion objects must be in the same file. Companion objects have access to the class's private information, and classes have access to the companion's private information as well. In this session, we discussed some of the magical properties in Scala. So have a seat, Mr. Potter. So let's create a runnable object called Magic Apply Scala, and we're going to create a class and a method inside of that class. So here we are. This is magicapply.scala, and we're going to create a class called foo. We're going to bring in a primary constructor of x as a type of int, and within here we are going to have a method called bar. All right, there we are. Now let's create a runnable object so we could try a few things. We'll call this one Magic Apply, and this will extend app. Great. Now let's get started. Val foo, there's the value name. This is going to reference a new foo with 10. And now what I'd like to do is print line this. Okay, so here's the question. I am creating a new foo with 10, and I'm calling foo bar with 20. What do you think this answer is going to be? Well, let's go to the command line and find out. Wow, seems that 10 plus 20 is 30. Isn't Scala amazing? So let's go back and try something else. Okay, in our code here. So this was 30. We know that. Now I'm going to change this method from bar to apply. Therefore, this has to change. So what do you think the result is going to be now? If you guess 30, you've got it going on. What was the point of all this? We've created this method over here called apply. And we know if we give it 10 as part of the state, then call apply with y, then obviously x plus y is going to return 30. Now, this is actually going to be a very important item when learning and understanding Scala. If your method is named apply, you can leave out the method name when you call it. In other words, I could call it like this. Both will be the same. So let's save it, and we have two 30s. So this shows you, if it's called apply, you don't have to call the method name as part of the instruction. Just call the reference and your parameter. Well, let's go back to the code. So where is this used in Scala? The answer is everywhere. And it's used for different behaviors, and we will see it as such when we discuss collections. For now, remember the last session for companion objects? We created a file called employee_design.scala, and we designed an object that had factory methods called create. Well, let's copy that over to our new folder chapter and open it. And if you don't recall this code, please revisit the session on companion objects in the last chapter. So here it is. Here's employee_design.scala. And this is everything that we wrote in the last session when we had talked about companion objects. See these right here? They're called create. Let's rename them to apply. Now we need to make sure in our runner that we also call it with apply. But what do we know about apply? We can just call it like this. Now take a step back. What does this remind you of? Case classes. So everything is coming together. We are able to create an employee. So let's give this a try. Let's compile it and run it to make sure that everything works as we specified. It compiled, and we get our date. Let's go back to the code. Pretty exciting, right? We have apply methods. We don't actually have to invoke it directly. We could just say employee and then just call the parameters. Now, let's create department. And remember, it was a case class. So we'll do this here. Let's say case class department, name and string. So here it is. Remember that? We did this a few sessions ago. And so in our employee design runner, let's create a couple of departments. The first one, well, we can test it out by saying department.apply sports. And on the second one, without the apply. So what are we trying to prove here? Well, I'm trying to prove that because we have a case class, that we're actually calling the apply method. Remember, one of the stated things that we can do with a case class is we don't have to use the new keyword whenever we instantiate an object. Now, there was a little bit something hidden about that, but now I'm clarifying what's happening. We're not actually instantiating something directly, we're instantiating something indirectly by calling the apply method. And that's why we're able to invoke something without the new keyword. That's the way it works. Now, let's save both of those as the print line. So we saved it, let's compile it, and now let's run it. Great, there it is. We could call it with apply, or don't call it at all. What a case class does for us, it creates automatically an apply method on the companion object. That's how all that works. Now, in our examples, we created an apply in a class, and we created an apply in an object. And apply is one of the most fundamental roles when it comes to learning Scala. In fact, I will say that this session is probably the most important one, or one of the most important ones, since apply is so prevalent and essential to learning the language. My rule is, if you don't visibly see a method name in something, it is very likely, highly likely, the method name that is being called is apply. And apply, as we saw in our examples, again, can be either in an object or a class. So over here, we had it in an object. But if we take a look at our magic apply, our apply is in a class. Could be an either or. So if a method is called apply, you don't have to explicitly call it. Just remove the method name. The method apply can be used in both classes and objects. And it's important to understand this concept, since it's so prevalent in everything when it comes to Scala. In this session, we discuss a simple topic, Infix Operators. Let's start off with a file called Infix Operators and try our hand at this Infix operator. So here we are in a file called infixoperators.scala, and the rule is if a class or object has a method that has one parameter, then you can invoke it in an infix way. Let's do our favorite class. Here it is. We have bar inside of this, and we'll add x plus y. Now, let's create a little runner here. What I'd like to do here is create foo with 10 and show the classic way of invoking that. Now let's try invoking that the infix way. So again, if a method has one parameter, then you can invoke it thusly. Foo space bar and then the parameter. Let's go ahead and save that, and let's go ahead and compile and run this. Here we are at the command line. And what I'd like to do is let's go ahead and compile our Infix Operators file. Oops. Well, this will probably likely work anyway, but let's compile it first and run the Infix Operators runner. There we go. And there we have it. We have 15 and 15. So let's go back to our code. We have 15 on both of these. Obviously, 10 plus 5 is 15, so that's why this foo.bar5 works. Again, we can display this in an infix way. Very cool, but let's say we have some multiple parameters. You could still kind of call those parameters in an infix way, so let's try it up here. Let's say we have not only bar, but baz, and baz is going to take two parameters, and this will be x plus a plus b. Now I say kind of infix. It's not going to look as clean as my lines 8 and 9, but it will work. Let's go down here and invoke that. Well, we can invoke that, say, with foo.baz with 10 and 14, and this is the classical way. If we were to do this in an infix way, we could do something like this, but we'd have to keep the parentheses. So maybe you would like it, maybe you don't. As far as this concerns, as far as the foo spacebar 5, that looks pretty nice and clean. Let's save this, going over to the command line. Worked out really well. Now, we've seen this before, and we've seen this in our introductory video on byte short, ints, longs, float, doubles, etc. And here we go. So let's go back to our code. And we've seen this before with the following. And remember, this was just an invocation of this. All we did here was use infix operators. I'll go ahead and assume that works. I won't compile it at this point and run it. But that works. We know that 3 plus 10 is actually an invocation. Remember, we can think of everything as an object in Scala. Really, this is the 3 in object dots. We're calling the method plus, and we're calling 10. Now in the JVM, it could very well just be the addition of primitives. Most likely that's what the case is, but when it comes to our code here, as the way we see it, it just looks like we're invoking the plus method on the 3 object. With infix operations, we can do something like this. Foo, this is essentially foo.bar for plus 19. Let's save this and let's take a look at the answer. We'll compile it and run it. And that's 33. Let's go back to our code. This says this was 33. So we're calling foo bar with 4. But foo was already 10, so that's 14. And 14 plus 19 is 33. Now let's say we're going to create another method up here. And let's play around with some more infix operations. And we'll call QX, which I hope that's how it's pronounced. And this too will bring in an int. And what we're going to do is we're going to return a new foo object with the new summation. Now, how could we invoke this? Well, since everything is infix, we can do something like this. foo.QX.space4. See how easy it was? I was calling it dot. We don't even need the dot. Foo space QX4, QX10, QX19, QX100 plus 19. And then after all this is invoked, let's say we want to finally call bar with 40. And let's say after all this, add 300. We can do this in a nice chain with spaces. We don't have to have a lot of parentheses and dots all over the place, all because of the infix operator rule. So let's save this and hope that works. Now let's go over to the command line. There we go, all using infix operators. Infix operators allow a method to be invoked without the dot or parentheses if there is one method parameter. Now, it could also be invoked with 2 or more parameters without the dot, but we would need the parentheses for it. Mathematical operations in Scala already use infix operators, and we've been doing it with add, multiply, subtract, divide, and modulo. In this session, we discussed right associative colons. This is another magical method property. So let's get started with a teaser. I'm just going to jump right in. And I'm going to create a file called rightassociativecolons.scala. Let's get started. Here we are in a file. I call the file rightassociativecolons.scala. I'm going to place this in a package just to change things up. And in this package, we will create an object called rightassociativecolons.extends_app. Now I'm going to create a class. And before all this, I used to create a class outside of the object. But let's say for this case, I want to create one inside of the object. I can do so. I could create objects inside of classes, classes inside of objects. I could have traits, abstract classes, wherever I want to, in whatever kind of organization I want to. That's how cool Scala is. So I'm going to create a class within here. I'm going to create a primary constructor. And within here, we'll have a def bar. And we'll do our trusty class of foo, thusly. Now, val foo is equal to new foo with 10. And now I'd like to ask, what is foo.bar with 5? All right. So there we go, rightassociativecolons.scala. So what do you think the answer is? Well, let's find out. Here's the compilation. And we get 15. All right, so I didn't expect you to fall for that one again, I hope. All right, so now what I'd like to do is I'd like to change this. And this time, we're going to do some operator overloading. So let's go back. Well, on here, instead of bar, I'm going to use an op character. We talked about this early on in this video series. I'm going to end it in a colon. Okay. Now, instead of bar, since we did rename this, what I'd like to do is invoke it with tilde and a colon. What do you think the answer is to this one? I went ahead and saved this. Think about that for a bit. Let's get over to the terminal. Oh my goodness, it's still 15. All right, that's still 15. Great. And now what we're going to do is we're going to add the following line to our source code. Let's go back. We know this works, and that's fine. There's nothing wrong with that. But what else we could do now is we could do the following. Let's compile and run it first, and then we'll come back over here. Okay, both are 15. So let's go back to the code and discuss. It's still 15, but it's written differently. The method parameter is on the left, not on the right. This only occurs if the method name, and I'm using name in quotation marks because it's not really a name. It looks like an operator. But the method name has a colon as the rightmost character, tilde and colon. What is on the right this time? Let me highlight that. What is on the right is the object. Well, that seems kind of twisted. Now, this only works if we're doing this as an infix operator. Infix meaning we have spaces right in here. Remember we talked about infix previously, where if there's one parameter, then we could have spaces and we don't need the dots or anything like that. That's what I'm talking about here. In other words, this is the non-infix way, and here is the infix way. But fear not, future Scala developers or Scala developers who are engaging in Scala right now, if this horrifies you, one or two things will happen. One is you probably won't see it this much, and two, well, you may come to embrace it. Now, just so you know, this is primarily going to be used in the Scala language for constructing and operating on lists and streams. I wouldn't say it's rare, but it's not going to be something that is going to plague your entire day. If the method ends in a colon, you may invoke it in a right associative way. In order to invoke it in a right associative way, must be invoked as an infix method. Right associativity is used for list and stream operations. In this session, we discuss option. Options are objects that represent yes and no. If you ask me if I have a middle name, I'd answer no, and hopefully you'd be satisfied with that answer. If you ask someone else what their middle name is, they'd probably answer yes. Of course, being curious, you'd want to ask, what is it? And most likely they'd tell you. That is option. It's also a way we avoid null. What is the point of null anymore anyway? It's ambiguous. Does it mean an absence of an error, or does it mean absolutely no? Who knows? Null was a disaster, and even the inventor of null will agree. Here's a quote from Sir Charles Anthony Richard Hoare, and he talks about null being the billion-dollar mistake. And his goal was to ensure that the use of references should absolutely be safe, with checking performed automatically by the compiler, and stated here he couldn't resist the temptation to put in a null reference because it was easy. This is why we use option. We don't like to use null. We like to use options with the some or none, defining whether we have an answer or we don't. Let's take a look at the relationship. Here's the relationship of option. We have option T, which is an abstract class and is a superparent. Therefore, we cannot make an instantiation of option T. And as subclasses, we have some T and none. All have a parameterized type. So I could have T represent a string or an int or whatever we'd like. Let's give this a spin. I'm going to create a file called options.scala, and let's go from there. Okay, so here we are in our file, and I'm going to get started. I'm going to create object options extends app. Now within here, let's get started with a sum. Great, that looks good. Now, let's try a different reference. So this is sum Antony. Now, just so you know, this is what we're actually calling. There is an object called sum that has an apply method. This is how we can create our option. This option is of a type sum. In other words, yes, we have an answer. But we could assign this to different kinds of references. For example, we could assign this to the supertype option string. Of course, we could be explicit about it and assign it to some string as well. Let's compile it and make sure that it works. Let's head over to the terminal. And I would like to compile options.scala. Now, let's run it. So far, so good. How do we work with none? None being we do not have an answer. There is no answer. Let's go back to the source code. On here, I'm going to create a none value. In case there is no middle name, we could assign that to none. We also have other references that we could choose as well. We could assign it to an option string. We could even assign it to an option of nothing. And if you've not seen nothing, all nothing is the subtype of every class. Very much like any ref is the supertype of every class, nothing is the subtype of every class. And that's why that works. But we could also assign it to the following. We have no middle name 2, no middle name 3, no middle name 4. But what is this none type here? Now, none is actually a singleton. It's an object. Let's go to the REPL and show you what this none type is. So remember, we had object my singleton, and this was a singleton. And I told you that as far as a singleton, you could assign it to a val or a var. And when we assign it, the type inferencer said the type for this is my singleton.type. Whenever you have an object, whether you create it from a new keyword or if you just have an object, there is a type that could be associated with it. And in this case, the singleton, mySingleton, which is an object, has a type of mySingleton.type, which is why this is assigned to none.type. None is actually an object, therefore the type for this is none.type. Let's save this. Let's compile and run the code again to make sure that we're in line. That looks great. Now, let's bring up an employee. We had employee before, and this time I'd like to incorporate the middle name with the class employee. Let's go back to our code. Within here, I am going to create a class employee, and this is going to contain a first name, a middle name, but the middle name is going to be an option of string. Last name will be a string. Okay, now we created this employee. First name is a string, middle name is an option of string, and last name is a string. So now let's do Charles Anthony Richard Hoare, since we were already talking about him, and we'll instantiate an employee from him. We'll do Charles. He has a middle name, Anthony, and finally his last name. Great. Now let's choose another programmer who does not have a middle name. C++ inventor, Bjarne Stroustrup. So here we go. Here's Bjarne. He has no middle name, and Stroustrup. There we are. So this is the way we interact with sums and nones. Let's save this, and let's make sure everything is looking good. Great. All this works out well, but we could model our employee better to hide the options when we create it. We're going to create some ancillary constructors, but since you know about factories, you could choose whatever best suits your requirements. Let's get started. Let's go back to the code. So here I am inside of class employee, and I'm going to create an alternate constructor or an ancillary constructor. In the first case, let's say we have a middle name. Let's say for this middle name, if we give it a string, and if we have a last name and we give it a string, what can we do? Well, we can call the primary constructor with the first name, and then for the middle name, let's wrap it up in a sum, and then include the last name. That's one way to go about it. Let's try a different scenario. This time, we don't have a middle name. In this case, we'll provide none. Now, in our last case, I had mentioned in a previous session that we can do some chaining. And let's say for this alternate, we have a no args constructor. In other words, no arguments are involved with this. Therefore, for something like this, since first name and last name are required, let's just say the first name's unknown. We won't provide any middle name, and then the last name will just make that as an unknown person. Now, this may seem contrived, but I wanted to show you how you can chain constructors all the way up to the top. This will call the constructor above it. Once there, this will call the primary constructor. Okay, so all this looks really good. Now, let's exercise it, and let's refactor the way we did Car Hoare and Bjarne. On here, we don't need the sum anymore, because if we give it a string, it's going to call the primary constructor with the sum. And of course, if we just call it with a first name or last name, this would make the middle name as none. And let's add a strange person here, and we're just going to create new employee. Now, let's save it. And this new employee, by the way, is just going to call the constructor with no arguments. So there we go, using ancillary constructors to create an employee. Now, to the terminal. That looks really nice and clean. Now, how about we get some information from our option types? Every option has a method called get, and get will get the information inside of a sum. But not every option type is a sum. We need to be careful. Let's pick on the middle name first. Let's go back to our code. We have this set up, and what I'd like to do is, given a middle name, I'd like to get the middle name. For the first middle name, it's easy to call .get, and that works really well. So let me save that, and I'm going to head over to the terminal, compile, and run. Obviously, we get Anthony, so if we call get, we can get what is inside of the option, or in this case, the sum. Now, we see that that works as planned. The issue happens to be when we try to get something out of nothing. Let's try that and see what happens. Let's go back to our code. Again, the problem is right now is if we have no middle name and we call get. Okay, so we get a no such element exception. That's why there's another method called get or else that keeps us from blowing up our code. Let's try that with no middle name. On here, I'm going to call get or else no middle name. Make sure our parens line up, and there we go. So I'm calling no middle name, get or else, and then the string that is going to be provided if we do not have a middle name. And in fact, we could do the same for both. Whether we have one or don't have one, both will apply. Let's make sure the parentheses match up and we're good to go. All right, let's save this, compile, and run. Great. First one says Anthony and the other one says no middle name. Let's go back to the code. I often like to make sure that the types match in the or else. If you're calling get or else with an option int, then I like to make sure that the or else is also returning an int. I'm sure there may be some other places where you would like to break that soft rule, but for the most part, I like to match up the types. So if we were to peel out the middle names for both Charles Anthony Hoare and Bjarne Strastrup, we could do the following. And we're going to be using the same methodology. We're getting middle name, get or else, no middle name. We're getting the middle name property, then calling get or else. So if Sir Anthony Richard Hoare does not have a middle name, he'll say no middle name. But he does have a middle name. And we're getting this via a property. Now, before things blow up, let's make sure that we have a val in front of all these. Otherwise, there won't be any property to get that middle name. All right, looks good. Now, let's do the same for Mr. Bjarne Strastrup. There it is. We'll get his middle name. And if he doesn't have a middle name, we will simply state there is no middle name. And of course, for our strange person, we will also ask for their middle name, get or else. And then we'll display whether or not they have a middle name. So everything looks good here. Let me keep this screen up for a minute or so that way you can absorb what we just did. We're using get or else. We'll go ahead and save that. Now let's compile and run. Great. Last three items are the print lines we just created. We have Anthony. That looks good. And we have a couple of no middle names. Looks clean. Now we could also solve this issue of peeling out the innards of an option with pattern matching. Although that would be too much work for little gain since get or else does the same thing. But we'll do it here for academic exercise. I gave a little bit of a teaser of pattern matching when we discussed case classes a few sessions back. So let's go back to our code and I'm going to create a method called peel the middle name. Okay, so here we are in our editor and we're going to create a method called peel the middle name. And this will accept an option of type string and this will return a string. It is a method, and let's say given this method, we want to take this X and we want to pattern match. To pattern match, we call match. Now we'll have different case statements. In case this is a sum, then what we'll return is the name. But in case it is a none, so we could do none or an underscore to represent anything else. In case it is a none, then we will also state no middle name. We have all this now. So this is a method. Give it an option of type string, and then return a string. Given that X, we'll match on it. In case it is a sum, we're going to extract the name from the sum and return that name. Otherwise, we'll just return the string, no middle name. Now, let's add a few more print lines to this. So we wish to peel the middle name for Charles Hoare and get his middle name out of there. We want to do the same thing for Mr. Bjarne Strastrup, and we want to do the same thing for our strange person. Okay, it all looks good. Let's compile. Let's run it. We have success once again. Anthony, no middle name, no middle name. Let's go back to our code and review. We have different ways of grabbing the information for options. Scala programmers don't like null in particular. We like our option types, and options are modeled as a sum or a none. Sum contains an answer to be extracted, very much like a fortune cookie has a little message for us inside. So does sum. None does not. Extracting the answer can be done by calling get or else, pattern matching, or we could use functions, which we haven't described yet, but we will shortly. Now, null is still available in Scala, and the reason it's there is because we need to interoperate with Java. Java is filled with nulls, and we can't necessarily ignore it. But if we're using a pure Scala application, if we're designing it from the ground up, everything Scala, then we avoid a null at all costs. In this session, we discussed tuples. A tuple is a container, and I'm intentionally not calling it a collection as far as Scala is concerned, just a container. For many languages, particularly Java, you probably felt the need to return two items from a method, and you thought, I have to either do an object array or create a list or some other kind of collection. or create a new class just to return these items. I just want to return 2 items instead of 1. Well, you could banish those ideas because Scala has tuples. So let's take a look. We're going to create a file called tuples.scala. Here we are. We're in tuples.scala, and we're just going to create a runnable app right now. We'll call it tuples, and we'll just make sure that we extend app. Given this now, what I'd like to do is create a tuple. And the way I'm going to do it is with a paren. And I could put in whatever I want. Tuples are heterogeneous. So this tuple here is just a container of the number 1 of the string cool and of a double 402.00. That's all it is. Just a container. You can put whatever you want in here. Let's give this a try. We'll save it. Let's compile it. Let's run it. Let's go to our terminal. So here we are compiling and works well. We didn't have any print line, but just knowing we could run it, we're in good shape. Now let's go back to the code. Just wrap up anything that you want in a parenthesis, and you're good to go. So how do we get at the internals of it? Well, we call t._1 for the first item. This is base 1. Why? Well, because of Haskell, that's why. Whatever idiosyncrasies you find with Scala comes from Haskell. Haskell, though, has methods called first, second, third, etc. So if anyone asks you why you do certain things in Scala that are weird, just let them know it's likely from Haskell. It is base 1, so I'm going to get the first item. Here's the second item, and here's the third item. The types for this is going to be an int, this is going to be a string, and this is going to be a double type. Types go along with everything in Scala. Therefore, this is a tuple with those internal types. Let's verify. Let's go ahead and compile and run it and see where we're at. Great. We have 1, we have cool, and we have 402. Let's talk more about the types. Let's go back to our code. Our val t is inferred. How's it inferred? Well, for example, one of the things that we could do is we'll just call it t1 here. Let's be explicit with the type. We could either declare the type as such. Remember, type inferencing took care of all this, so we don't actually need to do this. But for learning purposes, let's explicitly declare the type. This states right here that this is a tuple of an int, a string, and a double, and we could assign it to t. We could also do so as a tuple3 type. There is either a trait or a class called tuple3. I believe it's a class, tuple3, that has a parameterized type of int. Well, has a parameterized type of probably a, b, c, etc. But whenever we created our tuple here, it is a tuple of int, string, and double. 2 different ways to declare the type. So another thing that's interesting here is how high does it go? There are actually 22. So we have tuple3 here, but it goes all the way to tuple 22. No reason, just 22. Although I suspect if you're using tuple 22, it might be a good point in your life to rethink your design. Maybe you actually do have a need to create a tuple 22. So I'm going to go ahead and save this. Let's go to compile and run it. Great. All that works really well. Let's go back to our code, and this time we'll try other tuples. So what I'd like to do now is we're going to pick on tuple 2. So first off, let's create a case class for department. We created a department last time. This will have a name. It is a case class. And I'm going to create another tuple. This will be assigned to you. And the tuple will be for and department. And let's say our department is QA. Let's go ahead and save this. And what I'd like to do is take a look at the Scala API. So I'm going to head over to the browser right now. Okay, so here we are at the browser, and this shows tuple 2. You can see right here, this is tuple 2. It is a class, and this class, of course, has _1. That'll get you the first element. _2, that'll get you the second element. Tuple 2 also has this method called swap. And what that will do is it'll just swap the 2 elements inside. So let's try that. Let's head over back to the code. First off, let's display what U has originally. Then let's print line what swap has. And remember, all this is going to be immutable. In fact, you want to do this just to prove that everything is done immutably. Let's do that. And for the final one, let's just print out what U is. Let's save this. So what we should see here is we should see for department QA. After we swap, we'll see department QA and for. But just to prove that everything is immutable, U should still stay the same. Therefore, the for string with the department QA. again, because of immutability. Let's go back to the command line and run it. Great, there it is. So for department QA, that was you. Then we did a swap, so U2 is department QA, then 4. But just to prove to you that everything stays consistent, everything's immutable, when we print out U, it's just for department and QA. There's something about all this, and it's a smell of familiarity. What we did a few sessions ago in classes is we created a class called Couple, and it was exactly the same thing as Tuple 2. We actually engineered Tuple 2. Under a different name, again, it was called Couple, but everything is falling into place. We created our own tuple back then. We understand what this is. Again, it's just a dumb container. So some last notes about tuples. Tuples are sometimes pronounced tuples by other people. Everyone to each their own. Tuples are immutable. Again, we prove that. And tuples are integrable in just about everything in the language, and particularly when we discuss maps. Tuples are just dummy containers. They just hold stuff. Tuples are typed, very statically typed. If you extract _1, whatever type that is, we're going to get that type of int in return. There are tuples that go all the way to tuple 22. Tuple 2 is unique in that it has a method called swap, and it's only there for tuple 2. Obviously, tuple 3 does not have a swap. It wouldn't make sense. And tuples are immutable. They are an essential part in the Scala language. They are everywhere. In this session, we finally discuss functions. Scala is a functional programming language, and it's only logical that there should be functions. Thinking about functions, don't let this bring back too many nightmares. This is a function of x, as you've probably seen in your math classes before. And given this x, we could add 1 to it. So whatever x we plug in, if we plug in 3, this would be 4. If we plug in 10, this would be 11. Think of functions as functions from your grade school, middle school, high school, college mathematics. Give the function an input, you get an output. Now we're going to start things out the hard way. I'm going to start off with a file called functions.scala, and we'll start off from there. So let's go to our editor, and we're going to do the following. Object functions extends app. So this is going to be something that's runnable. Now that we have this in here, let's do the following. I'm going to create a function. And again, I'm doing things the hard way. And I'm going to use a function 1. What is a function 1? Well, function 1 is a trait, or as I call it, a pure abstracted construct or structure. And it has an abstract method within it. Let's take a look first. I'm going to go over to the Scala API on the browser. Here is Scala function 1. It is a trait, and traits, as I mentioned before, are constructs that have abstract methods, and it has one abstract method within here. Function 1 states right up here that this is going to bring in a T1 and it's going to return an R. Function 1, because it brings in one element and returns one element. It always returns one element. Every function returns one element. But this will likely be different. If you have a function 2, you'll have T1 and T2 that come in and R gets returned. These are parameterized types, and we know this now. And in order to implement this particular trait, we have to implement our own apply method. Keep in mind what apply does. Remember, we don't have to explicitly declare it. But again, I'm doing everything the hard way. Let's go back to our editor. And this type is, if you give me an int, I will give you back an int. That is the type. Now, I'm going to instantiate this. This is called an anonymous instantiation. And I'm going to instantiate a new object, function 1, from this trait. And in order to do so correctly, I need to implement the apply method. But I'm going to use an int. Why? Well, let's go back to the API. Because this has to be the same type as T1. And T1 is the first parameterized type of this trait. So let's go back again. And because the first item here is an int, we also declare it here. Therefore, this needs to be an int. And this is going to return an int. This int right here refers to this int. And this int refers to the return type. So therefore, let's just keep things simple. Let's just add 1. How do we invoke this function? It is called apply. Let's call it F1. So I'm going to call F1.apply, give it the 3, and hopefully what I get in return is 4. So let's save this. Let's go to our terminal, compile it, and run it. There's 4. Now, let's do some refactoring. Back to the code. We start things off with the obvious. One is, we know that because it's called apply, we don't need to explicitly declare it. So let's give this a try. Save it. Let's go to the terminal. Great. Looks really good. Now let's go back to our code. As a note, it's not always going to be like this, using function 1. Currently, we're on version 2.11.7 at the time of this recording. But as of Scala 2.12, these functions will turn into actual Java 8 functions. And as of 2.12, you cannot use it with older versions of the JDK. You'd have to use Java 8. And so all these functions are going to turn into Java util functions that are found in the Java util function library. Now, here's a fascinating thing about that. What do you think the method name is to invoke a function in a Java 8 function? That's right, it's called apply. And what a magnificent coincidence. This is going to be easy. So regardless if you're using 2.12 or 2.11.7, it's all going to work out. Let's come back to our code here. Why function 1? It brings in one parameter and spits out one. Again, it's always going to spit out one result. But there's function 2, there's a function 3, there's a function 4, all the way up to, guess what number? 22. There's even a function 0. That means you don't have to give it anything, but it's going to produce something for you. Let's try a few more functions. So here's the function 0 that I was just referring to. Function 0 does not require anything, but in this case, let's say we want to provide it an int. And all we have to do is run apply. And that's a function 0. Now let's try a function 2. Again, we're doing all this really explicitly. In this case, this will be a function that takes in an int and a string and will return a string. Again, doing things explicitly. This apply method is going to take in an int and a string, and what we're going to do is we're going to just take that string and append the x to it. You can kind of see how all these signatures work. Let's try them out. F1 we gave 3. We know that one works. We're calling F0. F0 does not require everything, but we do need to invoke it, so we need to make sure that we have an open and closed parenthesis stating that we wish to invoke this function. And again, for all of these, remember, we can do this. They are apply, so we could just leave that out. Let's save this. Now let's go to our terminal. And when we run it, looks great. We get 4, we get 1, and we get wow 3, so keep that in mind. Let's go back to the code. F1 works, we just gave it a 3, we're getting a 4 in return. F0 works, all we're doing is getting a 1 in return. And F2, we're calling 3 and wow. But wow, that was a lot of work. Let's change a few things up. First, we can declare the types differently. Let's get started with some refactoring. So these declarations right here can be simplified. Remember, this was function 1, brings in an int and returns an int, but we could refactor this to make it simple. What we're going to do is state here that this is an int, and we're going to use the rocket ship. I like to call it the rocket ship. And this one states that the type for this is something that brings in an int and returns an int. All this is a type declaration. That's all we're doing here. What is the declaration for this? Well, this one is something that when given a unit, remember the open and close paren, then will return an int. That's the type declaration for F0. In fact, we could get rid of some of these parentheses here. Now for function 2, what would this look like? If you give me an int and a string, I will give you back a string. Let's save this, and now let's go to our terminal to see if everything works as expected. Beautiful. Now we could also change the way our functions look. It's nice to understand how functions work and all, but really, let's release some of that sweet, sweet syntax sugar now and do some refactoring. All of this could have been taken care of with a shorthand. If you give me an int, then I would like for you to return x plus 1. For this one, if you give me a unit, I will return just 1. And for this one, if you give me an int and a string, I will return to you y plus x. All shorthand. Looks really good. Let's save it. Let's go to our command line. Fantastic. That looks really good. Now let's go back to our code. We're doing shorthand now. But remember, we have type inferencing. So let's pick on F1. F1 already knows that this is an int, and it already knows that when you add 1 to an int, it's just going to return int. We don't even need this declaration. F0 already knows that if you give it a unit, it's just going to return 1, and it already knows that 1 is an int. So let's just get rid of that declaration. Same goes for F2. It knows we're bringing in an int and a string, And it knows that when we call plus on a string with anything else, it's going to be a string. Therefore, we could just get rid of all that. Save it. Fantastic. Looks really good. Looks really simple. Let's go back to our code. Every function, I stated already, every function is going to return one result, always. That seems like a limitation. How do you think we could overcome that? Tuples. Tuples are excellent if ever we want to return more than one result from a function. Let's give that a try with a new function. I'm going to create a function called f3. And just so we know how things work here, let's create the type. I know it could be inferred, but let's create the type so that we have a better understanding. The type for this is going to be, if you're giving me a string, I could return to you a tuple of string and int. And this is going to return a function. Remember, right after the equals is the actual implementation. The actual implementation is, if you give me a string, I will return to you, and this is kind of interesting, I will return to you a tuple with the string and the size of that string. That's a lot of fun right there. Great, that looks good. Let's go ahead and save this, and let's go ahead and run this on the terminal. Neat, isn't that great? If we give it a string, we get a tuple in return with laser and the size of laser. That's fantastic. That's really nice to work with. We could get rid of the type because remember, we have type inference and it is done by the type system. Let's go back to our code. So in other words, to clean this up, we can just get rid of everything after the colon and before the equal sign. Because remember, after the equal sign is the implementation. Save it. Let's go to run it on the terminal. Again, all we did here was just get rid of the type declaration. We don't need it because it already states right here that this is a string. And it has enough information to know that x is still a string, and it knows that string.size is going to be of a type int. So it's able to deduce or infer that information. Now let's go to the terminal. Great. Lesson learned. You can return whatever you want from a function. A number, a string, a list, a tuple, an option, employee, you name it. Let your creativity soar when it comes to functions. So functions are a trait. You can think of them as pure abstract. Of course, you can have some concrete implementations in a trait. That's what makes it different. But mentally, if you want to think of it like that, that's fine. And functions are instantiated anonymously. Now remember, this is up to 2.11. 2.12 is going to be released shortly, and it'll be using Java util functions instead. The apply method in the function means that you don't have to call it explicitly. It was named as such intentionally. That way we could just call function and the argument. Now, while you could only return one item from any function, that one item can be a tuple in case you want to return multiple items. If you want to return a list or a set, we haven't gone through the collections yet, but you could do that as well. In this session, we asked the question, is it a method or is it a function? We discussed how a function is created and invoked in our last session, but there's always some confusion as to whether something is a method or a function. So let's analyze that. I'm going to create a file called method-or-function.scala, and let's give that a try. Here we are in my editor, and this is called method-or-function.scala. And let's get things started off. I'm going to create an object called myObject. We know what an object is now. And within here, I'm going to have a function. It's public by default, and this is a function that if you give it an int, and we already played around with something like this, and we're just going to add 1 to it. We have a method that states if you give that an int, then it will add 1 to it. They look the same, but they are different. F is a reference to a function. G is a method inside of my object that accepts an int. So let's create a runner. And what I'd like to do inside this runner is I'd like to invoke my object, and I'd like to invoke the function, and I would like to invoke the method. And this would clear some things up. MyObject.f, once I grab f, this is a reference to a function, then I could call apply to it. And let's say I want to give it 4, therefore this will be 5. But on the other hand, calling a method belongs to a context. This should be x, sorry about that. G right here, we're going to give it 4, and G is a method that's part of the myObject. It has a context. Context could be a class, abstract class, trait, or what have you. It belongs to a certain object. This is how they're different. One's a method, one is a function. Don't let this get too complicated. The f that you see here, val f, is very much like we had val a is equal to 40. No different. Whereas a is equal to 40 points to 40, f points to an object, an actual function object. A function as an object onto its own. And I mentioned back when we talked about methods, if it has a def, it is a method and has a context, always. G belongs to my object. And I explicitly put this apply here, just to let you know, all we're doing is we are retrieving the reference f, and then we're calling the apply method on that function. That way it makes more sense. And if it gets confusing to you, I recommend just using the apply call wherever you can. That way it makes visual sense. Let's run this as is first. So I'm going to save it, method or function.scala. Now I'm going to head over to the terminal, compile it, and run it. Now both of these are 5. Let's go back to our code. Well, one, we took the function out of the object, then ran apply on that function. Second one is we called a method with 4. They are different. And remember, when it comes to apply, we could leave it out. And this is the reason why I brought this lesson up. Because if you're just looking at these two, it looks rather confusing. If it gets confusing, just remember to put the apply there. That way you can have a good visual understanding as to what is going on. Let me go ahead and save this. Let's do one more run. Onto the terminal. Looks great. Functions are their own objects. Methods are not functions, and methods belong to a context, an object, a class, abstract class, trait, etc. Again, if it all gets confusing, you always have the choice. You could use an explicit apply. That way, it makes it less confusing. And over time, you get used to this sort of thing, and everything makes sense. In the last session, we saw a difference between a method and a function. In this session, we're going to discuss how to convert that method into a function. We want you to hold on to this knowledge because this will play a role a bit later. And I know it feels like cramming, but the relief that you'll feel when we wrap up this video session is going to be well worth it. So we're going to start off with a file called Converting Defs into Functions. And we will start again with our ever-loving foo class. Let's get started. All right, so here we have our editor, and it's opened up to a file called Converting Defs to Functions.scala. So I said we're going to start with our most famous foo class. Here it is. Now, our favorite method called bar. Foo has a primary constructor. We're going to bring in x. And as far as the method is concerned, we're going to bring in y of int, and we're going to add both of those. So we know how all that works. Now, I'm going to create an object, and we'll call this one Converting Defs to Functions, and this one will extend our app. Okay, let's get started here. What I'm going to do is I'm first going to set up foo. So here we go, new foo 10. Then what I'm going to do is the following. You ready? I'm going to take val f, I'm just going to call it f, and this is going to be assigned to x. Remember, x is the reference to foo, dot bar. But let's say I don't want to give it anything. What I wanted to do, and I'm going to use a placeholder here, is state right here, look, x.bar, I don't have the information for you, but if you can convert yourself into a function, I'll take this as a function so I could distribute it elsewhere. What I'm doing here is I'm taking a method and converting it to a function. The term is called partially applied function. Now I have this function, and now I could invoke this as a function. In fact, for things to be clearer, let's go over to the REPL. Here we are at the REPL. Let me do the same thing again. I'll try to be quick about it. Class foo, we're going to bring in an int. We have a bar. This will bring in a y. And we have x plus y. There's our class definition. What I did is I called val x is equal to new foo with a 10. And then I have val f is equal to x.bar, then underscore. Now, take a look at what the result is for this. F is now of a type function1. If you give it an int, it's going to return back to you an int. What we did is we converted bar into a function. Let's go back to our code. Now, since f is a function, and we already proved that to you by partially applying it, let's run it. Let's be explicit about it. Again, all we're doing is learning right now. Of course, we could call it either way, but these are functions. I'm calling f.apply with 20, and then here's f with 20. Looks good. Well, I'm going to go ahead and save that. Now, let's go over to the command line. All right, so here we are at the terminal. I want to compile converting defs to functions. Now, I would like to run it. Both are 30, and we converted them to functions. Remember, functions are objects that we have a reference to. Methods are bound to a context. That's important. Let's try a different scenario. Let's go back to our code. Let's say we have another class called Baz, and this will bring in an int. And within Baz, we'll have Qux, and very interesting in this one. What an interesting scenario. So I have a class Baz. This will bring in a z. I'll have a method called Qux that requires that we give it a function that if we give it an int, then it returns an int. This is our first setup. Now, let's just do a sanity call. Let's say val z is equal to new Baz with 20. And what we'll do is we'll do a print line with z. We'll call Qux with f. So what are we doing here? Well, we had foo to begin with, gave it 10, and then we partially applied it. So what we did was we called x.bar. That converted it to a function. Essentially, this is a function that we're going to add 10 to it. Then we have Baz, which is going to be given 20. So z is 20. And then we're going to call Qux with a function that we derived from foo. What did I just do? Maybe a little bit confusing, maybe not, but we're really exercising the language right now. We're going to take that f. Remember, essentially all that is a plus 10 function, and we're going to plug it into Qux. And since z is 20, what we should get out of here is hopefully 30. So now let's take this one for a spin. Wow, so very enlightening. Let's go back. See how we did that? We extracted a function out of a method, took that function and plugged it back into another object. Now, just so you know, we didn't even need to declare f. Let's say f did not exist. How would we call that? Let's say we're calling Qux, but this time we wish to call it with x.bar underscore. We're just inlining everything. This is essentially the same thing. And this too should have no problem. This should return 30. Let's do a sanity run. Great. Very, very awesome. Now let's go back to our code. I'm going to show you another magical moment. See how that underscore is right there? And it looks like it's definitely the last character in this method call as a method parameter, this underscore right here. If used as a method parameter, and if the last character is in an underscore, you can get rid of the underscore. So these two calls on my line 18 and my line 19, they're the same thing. Let's save that. Now, let's go to our command line and try it again. Works nice. Reason for this session is that often there's a misconception that you can use a method as a function, but that's not really the exact case. There's something going on in the middle, and that's the partially applied function. But once you understand the fine-grained details, you'll feel like you're in on a little secret. What if you have a method with two parameters, and we have one number, but then convert the rest to a function? You can still partially apply functions. So let's give this a try. Let's go back to our code. Let's try the following. Here we are in the editor. And what I'd like to do is I'd like to add another method right underneath foo. I'm going to call this one Jim. Not Jim as the person, but Jim where we go work out. So Jim is going to take two ints, z and a. And what we're going to do is we're going to take all that and we're going to say right here, x plus z plus a. Okay, we're going to get a little bit difficult along with this. What I'd like to do now is I would like to satisfy one parameter but not the other. Here we go. What I'm going to do is take val f2 this time. I'm going to call x. Remember, foo's already been set up. I'm going to call x dot Jim. And I'm going to state here that for Jim, for the first number, for z, I want to give it 40. But for the second one, I don't really know right now. But I want to convert that into a function. Got one number, but not the other. What could I do with this? Well, it's a function, and it's a function that if you give it an int, one has already been satisfied. This in turn is going to be a function from an int to an int. What can I do with this? Well, Qux loves this. It's asking, please give me a function that if you give me an int, that will return an int. So why don't I do that? Let me just plug that into here. That looks really good. Let's save that, and now let's run this on the terminal. Fantastic. Works all really well. Let's go back to our code. What I'd like to do right now, just so that way we could see everything, I'm going to copy this and paste it into the REPL. And I'm going to bring in foo and Baz. I like the REPL because we get to see the types here. That if I have foo 10, There's foo10, well, with 10 inside of it. And what I'm going to do is I'm going to create a function. So given x, I'm going to call gym with 40. And I don't know what I'm going to do for a, but I will just state that that will be an int. And this is what I want to show you. It shows you right here that this is a function. Give it an int, this will return an int, which happens to be the exact same signature that we need for Qs. Let's go back to our code. Let's say that Baz has another one called jam. And jam is requiring that if you give it 2 ints, then it will return an int for you. The implementation of this, we'll call the function with z and an arbitrary number of 10. So what can we do with this? Now for this one, let's do the following. Let's say that val f3, this time it's going to be x.gym with an underscore. And what are we going to do with that? Well, let's do a print line of z. This time we're going to call jam with f3. Z, remember that's from Baz. Z is pointing to a Baz object. It has a jam method that accepts a function, a 2 to 1, int to int. And it just so happens that if we call x.gym, remember, gym takes 2 parameters as a method and returns 1. The underscore is just going to convert that to a function. Then we could plug that into jam. Let's do a quick sanity check. Save it. Now let's go to the terminal. Very good. Very interesting. All of it works. But now let's clean this up. We didn't even need f3. What we could have done is just call, right within here, x.gym underscore. Again, the underscore is just going to partially apply all that. But what did we say about underscores in this position? We can get rid of it. Let's save it and go to our terminal. Same thing. We just inlined it, cleaned it up. Let's go back to our code. Now these videos are meant to be short, but you can certainly tell that we could go nuts with so many different combinations. It is certainly a thrill to work with Scala, and it's certainly a thrill to convert these methods into functions. Methods can be converted to functions using what's called partially applied functions. That was the underscore that we did. We use the underscore to turn the method parameters into function parameters. So if an underscore is the last character in a method parameter, just like we did a couple of times within the session, then we could remove the underscore. In this session, we discussed closures. Closures will wrap or close around an environment to compose a function. So let's jump immediately into the source code because visually we have a better understanding as to what a closure is. I'm going to create a file called closures.scala. C-L-O-S-U-R-E-S. Not like Clojure, which is another functional programming language on the JVM. All right, so let's head over to the editor. Here we are with closures, and what I'd like to do is create a class called foo, very similar to the one before, but I'm going to do a little twist here. Now, actually, the foo and bar that we usually use could be considered a type of closure, but I think this example will drive the point home a little bit better. So, foo and bar, but this time bar is going to be a function. We know how this works now. This is a type declaring that this is a function 1. If you give me an int, I will return to you an int. Now, the implementation is after the equals, and we have y, and we're going to go ahead and give it x, whatever is given as foo. Now, I'm going to create an object called closures. It could be whatever name we want. We'll extend app. Okay. So what are we going to do? Well, let's start off with m is equal to 200. It's a val, therefore it's final. We already know this. And now I'm going to do a val f, and I'm going to compose a function here that if you give me an int, I will take that x and I will add m. But m is coming from the outside. So what we're essentially doing here is we're closing around our environment. And our environment includes this 200. Give me an x, I'll take that x, and I'll add m. M coming from my outer environment, my scope. What am I going to do with that function now? So what we're going to do is we're going to create val foo, and we're going to create a foo object with 100. 100 is going to be the x that comes in here. And now what I'm going to do is I'm going to do a print line. Foo.bar, and I'm going to give it the function. So what's going to happen here? Well, foo is already 100, so x is 100. Then I'm going to call bar with a function. And this function is essentially plus 200. So therefore, since x is already established as 100, we're giving it a function that if you give it an int, this will just merely add 200. The 200 came from its environment. It closed around it. The 200 is outside of the scope of the function whenever we create the function in line 7. Now we're going to call foo.bar with f with that particular function, and what we should get out of it is 300. Because again, f is just plus 200 as a function, whatever int you give it. The int we're going to give it is the x that's inside of foo. That is a closure. And let's go ahead and save it, compile it, and run it. Let's go to the terminal. And we get 300. Let's go back to our code. Now some of you may be wondering something. What if m was a var instead of a val? Well, this happens to be one of the reasons we don't particularly like vars. And we wouldn't necessarily recommend it. In fact, I would just straight out say, I do not recommend it. And we will say this, it will not be stable. Every time m changes, it's certainly going to affect every invocation of that method. And we'll leave that up to you to try out to see what happens. But I'm not going to do that here because it would seem like that would be something that I approve of. I'll just let you try that out yourself. Closures are just functions that close around the environment. You can use any element within that function that references the outside world in its own context. That's what a closure is. And they're used to make up functions from that environment. And it's also best that you ensure that you enclose around something that is stable, particularly things like val, immutable objects. Over time, this is going to be something that will rescue your time because everything is known, everything is immutable, and everything is stable. In this session, we're going to talk about something you may have thought about already, but we'll put it into a session anyway. First off, we already know that we can take a function and put that into a method. But can we take a function and put that into a function? Answer is yes. In fact, it's called a higher ordered function. Let's get started with a file called functions with functions, and we'll try things out by plugging in a function into a function. Let's get started. Functions with functions extends app, essentially our main. Now let's create a function. So this function states if we give it an int and a function, then this will return an int. This is a function too, one that receives an int and a function and returns an int. And now our implementation. X is an int, y is a function that takes in an int and returns an int. And what are we going to do with this? We're going to take that y and feed it x. Now don't let this scare you. This is a function, again, that could take an int and a function. That could also take an int and return an int. Think this is useless? It isn't. The better you get with functional programming, the more acclimated you become with the Scala API, the more these kinds of signatures become second nature. In fact, let's do the following. Let's take this line and plug it into a REPL. As we see right here, this is a function too. But here's the thing, we don't have to be explicit with the type, and we can let the type system figure it out. Of course, we don't have to be explicit with this type. We can let the type system figure it out. That looks nice. So let's update our file and invoke it. Let's go back to the code. So again, we don't need this type. Just keep it clean. Now let's invoke it. We want to call the function f. We're going to call it with 3 and give it a function that brings in an int, and we will add 1 to it. Let's save that. Now let's go to the terminal and give it a try. And we get 4. Works great. Magnificent. Now, we could do some refactoring and clean things up. Let's go back to our code. Now, right in here, I'm declaring int. But as far as the signature goes, it already knows this has to be an int. So we can clean that up and just say, given an m, we will add 1 to it. I'm going to save it. We'll compile and run it. Great. Let's go back and clean it some more. So instead of coming up with a variable or a value name of m, we could just use a placeholder. That'll work just fine. If you're familiar with Groovy, this is analogous to the it or the it variable, meaning that whatever is coming in as a function, this placeholder will be used. It's saved. Let's give it a try. There it is. Addition is commutative, so let's go back. Commutative meaning that 3 plus 1 is equal to 1 plus 3. So what we could do, let's flip it. Now, what did we say about the underscore being the last item in a parameter? We can take that away. Let's compile it and let's run it. This compiled, but it says right here that we have a warning. So let's do what it says and add the flag feature. And it gives us some warnings. One of the warnings is that we are using a postfix operator plus. And we are. In order to turn that on, we need to import this statement. But it compiles. And in fact, we could run it. And we get 4. Scala has a lot of these features where all you need to do is import a certain class or package, and it's essentially turning on a feature and getting rid of some warnings. And that's what that import statement will do for us. I'm going to take that line and I'm going to paste that into the code. This import is stating we know what we're doing. Now we'll save it, compile, and run the code. There it is. This may be a little too concise. Let's go back to the code. Maybe even too terse for you. Take your time. Take your time as far as the team is concerned too. Not everyone's going to be at the same level. So even though this is a really neat feature, even though it's really short, sometimes things can be mysterious to others. No rush. Let's go to our next example. Can we return a function from a function? Sure, why not? In our next example, let's do the following. Here's an interesting example. So this is a function that if we give it an x, this will return a function. And that function is, if you give me a y, I'll add to the x that was originally provided. This happens all the time. In fact, we'll see it in the next session. This is bringing in an int, returning a function. I don't know if you could see it as well, but this is also a closure. A function is being returned, but it's closing around the x. It's using the x to make up this particular function and making it a part of the calculation. So let's use this. We could either invoke it like this, but if you want to be explicit about it, which sometimes I do recommend, just so that way we know what we're doing, these two are the same calls. Why do we want to do something like this? Well, perhaps for the first function, you want to provide information for a data source. That in turn will return a function. Then you could plug in an ID. Perhaps you're looking up a record. There are so many different reasons why you may want to employ this type of setup. In fact, this type of setup has a word. It's called currying. Let's save this and run it. We have two 9s at the end because we're calling them the same way, one with apply, one without. Let's go back to our code. Again, we give it a number, we get a function in return. We give that function a number, then we get the summation. Functions can take other functions in as a parameter. These are called higher-order functions. Higher-order functions is a term used in Scala, and it's used in other functional programming languages. And it's also used to describe when a method can take in a function. When a function can take in a function and when a method can take in a function. Functions can also return other functions. And this is useful for applying these functions in parts. In our last session, Functions with Functions, we used a function that returned a function. Let's revisit that here in a file called currying. In this session, we're going to talk all about currying itself. Let's create a file called currying.scala. Start from there. Here's our currying.scala, and I'm creating an object currying with extends app. Within here, we'll do some running. So within this, let's say that we have a function that takes in an int and returns another function that accepts an int and returns x plus y. And this is the function that we used at the end of our last session. So we get this, give it a function, then we get a function in return. That function takes an int, and we get something that adds everything together. Now, what if it wasn't engineered like this in the first place? Works out really nice, we could give things in parts, but again, what if this wasn't engineered like this in place the first time around? Well, that's where currying comes in. So let's say that we have a function that takes in an int and another int, so this is a function 2, and that returns an x and y. But let's say we want to provide this in parts. Well, what we could do is we can call f_curried. In fact, let's go ahead and take this and put it into the REPL. So here's valf. This is a function 2, brings in 2 ints and returns an int. And what I'm talking about here is calling curried. Now it's something that you provide an int, and that returns a function back to you. So let's go back to our code. What's happening here is that fc and g are the same thing. In fact, let's go ahead and bring in g into the REPL so we can compare. Here's g. This has the same signature as f_curried, or fc. That's what currying does. Breaks it apart so that we can feed this function in parts. So currying has nothing to do with the delicious dish with chicken. It has to do with mathematician Haskell Curry. He just had a delicious last name. His first name ended up the name of a language, Haskell. It's all pretty amazing, right? Now, if you want to bring it back into an uncurried state, you could also call function.uncurried to uncurry that function. What we had is, I'm at the REPL still, is if I had f_curried, this is what the curried function looks like, that if I call function uncurried of that curried function, it brings it back into a function 2, where you have to provide everything up front. So let's do that in our code. Let's head back. So in here, if I want to call F2 and set that equal to function uncurried, the curried function, then I will call println F2, and just to make sure that it is running, I'm just going to call F2 with 4 and 5. We know this is going to work. We saw the signature on the REPL. Let me go ahead and save that. Let's compile and run it. And there's 9. Let's go back to our code, and there it is. A note here, again, FC and G are the same function. We took F and curried it. That changes it to a function that takes an int and returns another function. Currying is taking a set of arguments and turning them into a sequence of functions, returning functions. You can convert an uncurried function into a curried function by calling curried on that uncurried function. You can use the object function, its method uncurried, to uncurry a function. Currying is named after mathematician Haskell Curry. And that sums it up for currying. In this session, we take a look at currying once more with curried method parameters. Curried method parameters group parameters by logical groupings. Can be in any form, groups of 1, groups of 2, groups of 3, etc. So we're going to start off with a file called curriedparameters.scala. And in there, we'll try varying forms. Let's get started. Here we are. We're in a file called curriedparameters.scala. And I'm going to create an object called curriedparameters, and this will extend app. This will have 3 methods. One, we'll take x, y, and z, and we'll add them up. Next one, we'll call bar. But this will be as curried method parameters. Finally, we'll have baz, but what I'd like to do here is just group the first 2 and leave z as its own individual group. The implementations, though, are all the same. They all result to the same thing, foo, bar, and baz. But how they get evaluated is different. What I'd like to do, let's copy these 3 and paste them into a REPL. Here we are in the REPL, and we're pasting them in. Foo has a signature where we give it 3 items and we get an int in return. It is a method. Bar is curried. We can give it x, y, and z separately. Still gets evaluated the same. And you can tell with baz, the groupings are, the first 2 are ints, third one is an int, and this returns an int. Where this becomes different is when we start partially applying these methods. So if I have f here and call foo with an underscore, this turns into a function. Remember, we used this before in turning methods into functions. This is going to turn this method into a function 3. 3 in, 1 out. Or let's try bar. This one's different. This one's fully curried once we partially apply this. If we give it an int, this returns a function. We give that function an int, that returns another function. We give that an int, we finally get our int. But of course, if we call baz, this states here, if you give it 2 ints, it'll return a function. And if you give that function an int, it will return an int. However you want to organize these methods is up to you. Where else would you find an advantage in investing, making your calls like this, is when you call the methods with 1 argument and wish to partially apply the rest. So let's compare that in our curried parameters file. Let's jump over to our editor. So given that now, let's do the following. Val f, and what I'd like to do here is I would like to, in this example, I would like to state that 5 is the first number, but the rest I don't want to provide right now. Well, if they were uncurried, this is the way I would have to go about it. But for bar, which had curried method parameters, I could do bar 5 and then underscore. These 2 are kind of the same, not really. We'll show that in the REPL here shortly. But this is partial application. In fact, what we could do, let's go ahead and bring this over to the REPL. So here's foo, the original one. F is a function 2, bring in 2 items, return 1. But the bar 5, remember bar is every item is curried. Therefore, this is going to turn into a function that if you give it an int, it's going to return a function back to you. Signatures are vastly different. So this is why you may want to choose between one versus the other. Do you want to partially apply each one, or do you want to use curried methods? How we invoke this is different. Let's go back to the code. Let's say that we want to call f with 4 and 3. That will work just fine. With g, though, remember this is still curried, so I have to give the parameters in parts. And if that looks too mysterious to you, all we are calling is this. Remember, currying is just returning functions. So if it becomes too mysterious, add those applies and gain some clarity. We went ahead and saved it. Now, let's compile and run it. And there we go, 34. Why? Because we first established 5, then 10, and 19. You'll be seeing this pattern signature a lot in your endeavors with Scala. One of the things that you can use this for is particularly with implicits. Unfortunately, there's no time or space in this video series to talk about implicits, but implicits are always called via a curried parameter. It needs its own separate section. So this methodology you'll be using quite a bit. Curried parameters form groups of parameters, and we've seen that. Curried parameters make partial application a little easier, and curried parameters are often used with implicits. Again, we don't have time or space in this video series, but when you discover implicits, that would make things a lot easier and the way to go. In this session, we discuss by-name parameters. By-name parameters are tough to describe till we start coding, of course. There's some good blogs out there, but hopefully in this video series, we'll have a fuller example and hopefully enlighten rather than to confuse. We start off in a file called bynameparameters.scala. Let's go to our editor. Here we are in our editor, and I'd like to start off with object, and we'll just call this byname parameters, make it something runnable. Extends that. Now, we'll just treat this like a story, and there are three sisters, by value, by function, and by name. So we start off with the first one. This one's going to be called by value, and we're going to bring in two curried parameters. And what I'd like to do with this is set up a little side effect here and stating that we're in the by value method. And from this, we're going to return that what we've done is added x plus y. Next one is by function. By function, we'll take in an int and we'll take in a y. And this function will start off with a unit and return an int. And we'll do a print line here and call that one by function. And we'll call x plus y, but y is a function, so we need to call it like this, and then close the brace. So that's by function. Again, we're giving it an int, and we're giving it a function to run. Next one, we'll do by name. By name, we'll give it an int, and give it somewhat of what looks like a function and behaves like a function, but it's a by name parameter. And this is going to be, and you could still think about it as a function that's going to return to an int, and we'll do a print line and call this one by name. And this we'll call x plus y. All are curried. Now let's start with by value. By value is the eager of the sisters and demands two ints and adds them together. How would that look? Well, let's get started. Val a is equal to by value, and we wish to invoke this with 3 and a block that says print line that we're inside of the call and 19. Okay, so we're going to call by value, and then y is going to be accepting an int. Problem is here is it's eager, and this is going to be evaluated. We're going to see int call first, then by value. So let's save this, let's compile it, and let's run it. So on here, let's call Scala C by name parameters.scala. Now let's run it. So there it is. It says int call by value. Let's go back to the code. Remember, all this is eager. Before y gets its result, it's going to evaluate this block. That's why we have int call first, and then it's going to take that 19 and then add 3 to it. That's by value. Eager indeed. Now, by function is lazier than by value. And in the second parameter, this will evaluate whenever this particular sister pleases. All she asks is that you give her a function 0, and she will get what she needs when she needs it. In other words, this will be a function, and it'll be lazy, so we'll get by function first, and then it will evaluate the function y, get what this needs, and then add it to x. Let's invoke that. This one we'll call b, and we'll call, in this example, instead of by value, we'll call by function. Except when we do this, this has to be a function, so it has to look like this. And in fact, all this needs to be wrapped up. The block has to be in here, and then finally, we'll wrap things up. So a lot of work going into this one. Let's give this one a try. We're calling again by function with a number and a function. And this function is a function 0. In other words, we don't need to give it anything. And what this is going to do is it's going to invoke this function. And what it's going to return is a print line as a side effect telling us we're inside the call now. And then it's going to retrieve the 19. We'll get our laziness, but we'll get not as a clean a call as line 8. As you can see here, a lot of extra work. So let's go ahead and save that. Let's compile and run. We see something a little bit different now. We see this laziness. We get by function first, then we're inside of the call. Let's take a look. So as opposed to this one, which in call appeared first, then by value, over here, by function occurred first, and then it called this function. So that's really good. But where it isn't good is how we called it. Obviously, we have this long call. We had to set it up, make sure the parentheses matched up, and the like. I really like the way we did this call, except this call was very eager. I still want it lazy. I want it to be evaluated when it needs it, not before the method is executed. Again, it'd be nice to have the delayed laziness of a by function with the ease of calling it with a by value. And this is what by name is for. So under by name, what we could do is the following. We can call by name, and we'll have our number here. And then what we could do is very much like A, is we could say print line in call and 19. Again, the laziness and the clean call like we have under line 8. Let's save this and let's run it. So we have the laziness and we have the nice looking call. In fact, for the nice looking call, let's go back. Since these are blocks, we could get rid of the semicolon here and just treat this all as one block. That looks really nice. Here's that, and here's that. Looks a lot nicer with multi-lines. It looks like we could just add a block to this, and we could do this for both by value and by name, but by value is eager, by name is lazy. Of course, the by name sister wins our hearts. She lives happily ever after, and we award her with an Arduino. That's what a by name is. Again, gives us the easiness of calling it, and the laziness with a delay. So whenever Y is called, that's when this block is executed. Let's go ahead and save this and run it. All looks really well. So let's go back to our code. Now we're back at our editor, and I'd like to create something a little bit more substantial, a little bit more real world. What I'd like to do is create another method in here called divide safely. Now we have a lot of information under our belts. And what I'd like to do is provide this with a block that is going to return an int. And if everything calculates correctly, I want to return a sum of that int operation, otherwise a none. Well, whatever mathematical operation I give it, let's say I want to try to calculate that one particular function. Next, I will have my catch. We already described try and catch, but over here we want to try and catch, and we want to catch different exceptions. And in case it's an arithmetic exception, what I want to do is return none. We'll run our function. Whatever our function returns, this will be an int. And if it calculates successfully, we'll return it and wrap it in a sum. If it's a failure, we'll return a none. There are other types that you can use for this. We're just using option because we know it. But there are others called a try and an either. Those are actual types. We don't cover it in this video series, but you can take a look at the API for more information. So we have our opinion here, and what I'd like to do is give this a try. Val D is going to be called divide safely, and now because this is a by name parameter, we can treat this like a block. And in this divide safely, let's say val x is equal to 10, val y is equal to 5, and we'll do an x divided by y. And when we do this, this should return a sum of 2. Let's do E, and let's do something dangerous with E. Let's say we want to divide that one safely. For this one, I'm going to state that val x is equal to 1000. And again, this is a block. We can do whatever we want in this block, and we'll do an x divided by y. And for that, we will print line E. Pretty cool. So we're making use of options, and we have our blocks. Let's save it. Let's keep the code here for the viewers. Take a better look at it. Again, we have a by name parameter. Again, we could treat it as a block. We could also treat it as lazy. In other words, we don't need this evaluated when it's called. We'll wait until this point right here. We have the laziness and we have the cleanliness of this call. Save it. That is some beautiful stuff. First one was 2. It was wrapped in a sum. Second one ended in error. We had to divide by 0. So that returns a none. This works great if you want to clean up resources or if you just want to wrap things up in a try-catch block. Whatever it is, the by name parameter comes in extremely handy. By name parameters are parameters that can be called as a block and are lazily evaluated. And by name parameters are outstanding for catching exceptions and cleaning up resources when you are done. This is not really a programming session. This is just a little bit of something before we enter into talking about collections. Now, what won me over about Scala is the cleanliness of the API. And this is very important to me. Scala does a great job in making sure that the methods that you have for list also applies for sets, strings, also streams, vectors, arrays, and so on. In the Java side of life, you tend to see cracks, and nothing wrong with Java. Java is an excellent programming language. It's been around since 1995, and some layers have been added over time. And with that, some of the things are, we'll just say, incongruous. It's really hard to try to keep it all into memory. I think Scala can be a difficult language to learn, but I think once you come to the collection side of things, all of a sudden, things are going to start dropping off as far as the learning curve is concerned. Because once you learn things like map, FlatMap, reduce, fold left, ForEach, all of a sudden the knowledge that you acquired with list can be applied to a stream, to a set, to a map, etc. Let's take a look at the Scala API. Let me show you what I mean. Here's the Scala API. This is list, and it gives some examples, which is great. But take a look at some of these methods, and we'll be using some of these. There's plus plus in here, but let's use some words here. There's apply, there's collect, there's contains, there's count, there's drop while, there's exists, filter, filter not, flat map, flatten, fold right. You see all these methods, and they all mean something. And once I know either all of them or most of them, I can take the knowledge that I've acquired for list, and I could apply them to something like a set. So here's set. Set also has plus plus. Remember, we saw that with list. There's also an add string. There's also a collect. There's also a drop right. There's equals. We talked about filter and list just right now. There's filter not. You see the same methods, but applied to a different collection. Let's take a look at string. Well, actually, it's called string ops. And take a look at the methods here. There's plus plus. There's add string. You have a few ones that belong to string itself for character manipulation. But you have drop. There's drop right. There's ends with. There's exists. There's find, there's fold, there's for each. All that's in here. There's a flat map, there's the find, there's the filter not. So as I said right here, the lists, the sets, the streams, the strings, the vectors, all of these have essentially the same methods. Once you learn one, you learn them all. This is what I mean. You get a precipitous drop off in the learning curve right now. Yes, you are going to have to invest in learning one of these, in one of these collections. But once you get a handle on it, the rest becomes very easy. In this session, we're going to talk about lists. Lists are an immutable collection with duplicates and index access, also very searchable. Let's dive right into the code. We're going to create a file called list.scala, make it a runnable object, and then play around with the lists internally. Let's get started. Here's our file, list.scala. We'll extend app from it, and let's go creating some lists. All right, first time around, let's create a list. And this is the way you see it inside of most books. You'll see something like this. List 1, 2, 3, 4, 5. But you'll probably be thinking, wait, what is this call? Where is this coming from? Well, let's take a look to see where all this is coming from. Let's look at the API. Here's the Scala API, and this shows the list. Now, over here on the left-hand side, you see O and you see C. That means this is an object. That means this is a class. In fact, take a look at this label right here. See how it looks like a sticker and it looks like something's underneath? Let's click on that. This is the companion object. We had a video earlier in this series talking about companion objects and what they do. Now let's take a look further in. This is what we're using to create our list. Notice the name, apply. What you may have not seen before is this star right here. This is called a repeated parameter. That just means we can have 1, 2, 5, 20, 100 different elements on here, and they all have to be of a type A. And what do we get in return? A list of A. Let's go back to our code. When we create a list, these two are the same thing. This is a way, or at least one way, we can create a list. Another way we could create a list is by the following. Hold on to your hats on this one. Whoa, what's going on here? Well, let's go to the REPL and describe this. I think it's a lot easier that way. Here we are in the REPL. Nil has nothing to do with null. Nil is really an empty list, and it tells you right here. And then what did we do? We called 1, 2, 3, 4, 5, and nil. And this created for us a list of 1, 2, 3, 4, 5. And this list is parameterized. It says it's a list of int. But what is nil? And what are those double colon? We know what nil is now. It's an empty list. But those double colons are interesting. They are actually methods. Methods that end in a colon. We had a section earlier called write associative colons. And we talked about methods that end in a colon and what that means. That means it's write associative, meaning the thing we have to pay attention to, the object we have to pay attention to is this nil right here. When we create a list, let's start off a little bit by a little bit. This gives me a list of 5. This is the method parameter, this is the method name, and this is the object we're operating on. It's the same thing as stating this. Remember our discussion on infix operators? If we do 4 colon colon 5 colon colon nil, that's just a list of 4 and 5. If we do 3 colon colon 4, 5, and nil, this is just a list of 3, 4, and 5. And obviously building on that till we get what we had before. 1, 2, 3, 4, 5. That's how you create a list. 2 different ways. In the earlier days before 2.8, you'd probably see this format a lot more, but the more modern way is doing something like this. But still, you have a choice. So let's try some methods. Let's go back to our code. One of the important ones when it comes to a list is head. We're going to pick on A for a while, and A.head is going to return 1. Next one is the tail. Tail is going to be 2, 3, 4, 5. If you're an old Lisper, this used to be called car and cutter, probably still is. In Scala, it's called head and tail. Scala added a couple more methods that you can use. One's called init. That's going to be 1, 2, 3, and 4. And last, that will just be 5. Now, head and tail are quite essential in functional programming. They are used for a lot of data processing, used in a lot of recursion. That is a mainstay in functional programming. Scala just added init and last, and can be useful at times. So let's just save it right now. Let's make sure everything works. Head is 1, tail is 2, 3, 4, 5, init is 1, 2, 3, 4, last is 5. Okay, now I want to retrieve the 4th element out of this list. Retrieving information is 0-based, so the 4th element would essentially be the last one. Or in fact, let's say we want to do the 3rd one. Let's go back to our code. So, in other words, what I'm stating here, let's go to this code over here, is this is the 0th element, this is the 1st, 2nd, 3rd, and 4th. Let's say I want to get the 3rd element. I want to get this 4 out of here. How do I go about doing that? Well, any book will tell you, just call A4. What a lot of books don't tell you is, what does this mean? What am I calling? Remember, when in doubt, and if it looks weird and you don't know what you're calling, try adding .apply to it. That's exactly what we're calling. Now, let's take some time out here and reflect what's going on. Here's list apply, but remember, this one was from the companion object. And when we talked about apply, we talked about how apply could be used in an object or in a class, which in turn will be used in an object as well, but not the companion object. And so what we're doing here is we're calling apply on the list itself. One is the companion object, and one is the list itself. Let's go to the Scala API and take a look at the information on what apply means. We're in the companion object right now. It says O right here. Let me click on this so we can switch over to the class. And the apply we're talking about is the one in here. And here it is. Def apply and int returns an A. Now, A, where's that from? Well, that's a parameterized type of this class. It says so right here. If we say a certain list, or A, what we called it in our example, open paren 3, close paren, this is going to get for us the 3rd element. Back to our code. And say, I just called it 3, so why don't we just use that? This will return number 4. Let's try a few others. We can ask for the minimum one. We could ask for the maximum. We could ask if it's empty. We could ask things like, is it non-empty? We used that one previously. If we want to update one item in there, we can call updated and say, for the 3rd one, I want to replace that with 100. But all these are going to return a copy. So if I call A updated, it's not going to update this actual list. It's going to return a copy of it. I will tell you this, though. This one's kind of underused. I don't think you're going to use it as often as you think you will. So let's save all this and let's run it. Or let's see, what is A again? What are we looking at? This one is 4. Okay, so 5 and 4. And then we have the min, the max, is empty and non-empty. So there we go. This is the min. This is the max. This one is it empty? False. Is it non-empty? There it is. And here's the updated. What we did here is we specified on the third element, we want to replace that with 100. Now, let's talk about makeString. Now, makeString is available on lists, sets, streams, maps, etc. All the different collections. I'll talk about it here because we're going to make use of this throughout this particular chapter. All right, let's go back to the code. MakeString is a wonderful utility. In fact, I can no longer live without it. And this one, what it's going to do is it's going to take a list and convert it to a string with comma separating each item on the list. If I wanted to separate each item with, say, a star star, I can call makeString with that star star. If I want to bound the entire list with, let's say, a bracket, I can do so. MakeString is a wonderful utility for us to use. Let me go ahead and save that, and let's run it. And remember, it's going to be the last three items when we run this. There's the makeString with a comma, third to the last one. There's the makeString with a star star to delineate or as a delimiter of each item. 1 star star 2, star star 3, star star 4, star star 5. Finally, the third one, we specified what bounds there are. So the left-hand side is going to have a bracket, right-hand side a bracket, 1 star star 2, star star 3, 4, 5, etc. A great utility. And again, I don't want to confuse you by saying this is only a part of lists. It's a part of set, part of map, part of just about every collection there is out there. Lists are immutable collections. Duplicates are allowed. You could access by index. How we did that was we used apply and searchable. We discovered that nil is an empty list. Lists can be created from a companion object using the apply method. I don't have a bullet on this one. We created a list using : and nil. Two different ways we can create a list. And lists have many of the same functional properties as other collections. We just discussed makeString, mkstring right now. We can use that makeString for sets, maps, etc. All about having a clean API. Sets are a collection that have no duplicate elements. They're also powerful and they generally have more mathematical methods because they are sets. They don't maintain any order, therefore calling head, tail would be a little bit unreasonable with it. And apply also has a different behavior. Let's get started with sets. I'm going to create a file called sets.scala and let's try some sets out. Here's our object sets. Let's get started with a set. I'm going to call set 1, 2, 3, 4. Set of 4 elements. Now, as I'm creating this, take a look at the signature. Set and the number of elements. What are we looking at? Well, if you remember from list, what we're looking at is actually a companion object .apply. Let's take a look at the API. Here's the API, and here's set. Let's go to the companion object. Set right here is a trait, again, very much like an interface. You click on the T, and now we have it as O. This is the companion object. And now within here, we have apply. That's what we're calling. And this is a repeated parameter, so we can have 1, 2, 10, 19, 100, however many number of elements as we want. So let's go back to our code. We'll do 3 elements here. Let's create another set 2. I'd like to show you something really interesting. So we'll have 5. Let's try another one. This one will have 5 and 6. And finally, let's have one with some duplicates. So 2 6s and a 7. Or at least we'll give it a duplicate. That doesn't mean at the end result we will have a duplicate. Now all of these are using apply, and we see that now. So in other words, we could have just easily have called apply. Now, what I'd like to do is take a look at them. All right, we're all set. We created 4 different sets, all with varying sizes. The last one, we gave it duplicate values, and we'll see if it got rid of them. Now, let's go ahead and run it. Let's go ahead and compile sets. There we are. The first one was 1, 2, 3, 4. That's what we gave it. But afterwards, then it's starting to mix things up. With 6, it's starting to mix things up even a bit more. And by the time we add the one with 7, and remember on that last one, we gave 2 duplicates of 6. So we have different arrangements. But these are all sets. And again, the order is undetermined. It could be whatever it wants. That's how we create sets. But take a look at the top one here. I have 1, 2, 3, 4, and then it starts getting mixed up. Just kind of a weird thing about Scala is that if you have 4 elements or less, they are going to be ordered. But once you surpass that, then it starts moving things out of order. Just something I noticed and just thought I'd share. Okay, now head back. Let's try a few things. I'm going to create another set here. This will be called set 5. And set 5 is going to have a set of 1 and 2. All right, that looks great. Now what I'd like to do is try some of these operations. Let's say we have a set. Let's use the set of 1, 2, 3, 4. and ask what's the difference with it against set 4. Now, this shows the difference between two sets, but it's based on the left-hand side. So the set on the left has 1, 2, 3, 4. Set 4 has 1, 2, 3, 4, 5, 6, 7, etc. Is there anything different in set 4 that we don't have in set? The answer is going to be no. So this is going to be an empty set. Let's reverse it. What is different from set 4 that's in set? So set 4 has 1, 2, 3, 4, 5, 6, 7, but set only has 1, 2, 3, 4. So it stands to reason that this set that's going to be returned is going to contain 5, 6, and 7, or some kind of arrangement thereof. Let's give it a try. We'll go ahead and save that. Now, we haven't used set 5 yet, but we will. Let's go over to the command line. And there it is, 5, 6, and 7. Second to the last one's an empty set. The last one is 5, 6, and 7 because set 4 has 5, 6, and 7. And that's different than set. We could also use a union, and this is the combination of two sets. Let's go back to our code. Given a set of 1, 2, 3, 4 and a set 3 of 1, 2, 3, 4, 5, 6, what is the union? Well, that's the union. And remember, there are no duplicates along with this. Save it and verify it. So 1, 2, 3, 4, 5, 6, of course, order is indeterminate. That's union. Now, let's talk about intersect or intersection. Let's go back to our code. This will show the intersection, or what we have in common. So what do we have in common between set and set 3? Well, this would be 1, 2, 3, and 4. We'll save that. Now let's take a look. There it is, the intersection between set and set 3. Now let's try the set 5 that we created earlier. What is the intersect of set 5 with, let's say, set 4? Set 5 only has 1 and 2. Set 4 has 1, 2, 3, 4, 5, 6, 7. The intersection of that should just be the set of 1 and 2. Let's give it a try. Beautiful. Now, we could also use plus plus. Let's go back to our code. So instead of union, we could have done plus plus. The only difference between union and plus plus is that a union only works with other sets. Plus plus works with any kind of traversable. That means if it's a set, a list, or some other kind of list structure, then we can use it. Let's try an example. So again, this works the same as a union, and this will be a 1, 2, 3, 4, 5, or any combination of that. But since it accepts any other type of collection, then we can give it a list of, let's say, 15, 19, and 20. We talked about list in the previous session, so let's give that a try. Now this one is going to be, before we run it, let's say set is 1, 2, 3, 4. So this would be some kind of combination of 1, 2, 3, 4, 15, 19, and 20. It's not going to preserve that order, but it'll have those elements. We'll go and save that. Let's go to the command line. Now, if we want to remove items from the set, let's give that a try. Let's go back. Let's say we want to take our original set and we want to remove set 5 from it. Take one set and deduct it from the other. Let's say in this example, we want to take this set and remove another set, 3, 4, 5. And as another example, let's do one number. Now here's the difference between plus plus and minus minus and minus. So if we have two operations like this, that means that the parameter has to be another collection. Just like over here, I have set, I have minus minus, and this has to be another collection because we are using minus minus. If we're using as a parameter a single item, like number 3, then we just use a single minus. That's typically the convention. So let's give this a try. We'll go ahead and save it, and let's take a look. It looks great. Now, let's talk about apply. Let's head back. For apply takes on a different role. Let's take a look at the API. Here we are at the API. We're already looking at object. Let's switch this over to the trait. And taking a look at the trait, this trait also has an apply. But it's different. Remember, list got the element from a certain index. But we don't have that kind of lookup when it comes to a set. But what this will ask is it will ask, test if some element is contained within this set. So essentially, it's very much like the contains method right up here. Let's give that a try. Let's head over to our code, and we could do the following. Set.apply. Now this isn't going to get the fourth element. We are merely asking, is 4 contained in this set? Again, let's take a look at apply. Make sure that everything works correctly. Apply has to be an element of A. Given the set of A, it has to be of that type. Our sets are all ints, therefore the element must be an int. And this will return true or false. Let's go back. This set that we're talking about is a set of 1, 2, 3, 4. Obviously, if we call apply with 10, that would be false. If we didn't want to use apply, we could have used contains. Let's save this. This right up here should be true and the rest false. Go ahead and save that. Let's compile. Let's run. Great. Sets are collections with no duplicate elements. There's no search by index. We can't just say, here's the index, get me what I need. Fast querying works really well mathematically, and it's unordered. Sets typically are more mathematically powerful than lists, and apply has a different property. This will return true or false if an element is contained within that set. In this session, we discuss maps. Maps are often called in other languages associative arrays, dictionaries, tables. A map in Scala is a table of keys and values. Items can be looked up by key. Once you establish that key, you get a value in return. Let's try some examples. Okay, here we are at the editor. I'm going to create a file called maps.scala. Val m is equal to map, and we'll just go ahead and state apply. Let's take a look at the API. So I'm going to call map.apply, kind of the same rules as we had with lists and sets. But let's take a look at the signature and the reason why I want to bring it up on the API. This has a companion object. Let's take a look at that. So we know there's an apply, but let's take a look at the signature. Apply has two parameterized types, A and B. A stands for the key, B stands for the value. And what do we need to give it? This says that this is a repeated parameter of tuples. And this is very powerful because you don't have this sort of thing with Java. In Java, you don't have tuples. Therefore, you can't create maps very well with ease unless you use a library like Guava. But in Scala, you can create a map in a nice one-liner. And this, in return, will provide us a map with a key and a value. A, again, representing the key, B, representing the value. So, let's take this knowledge and build our map. First shot of this, we know that this can only accept tuples. And let's say, given an integer and a string for a value, this is one entry. Second entry will be this one. And here's the third entry. This will create a map for us. This is legal. But, just like as we stated before, what we know about apply is that we don't need to explicitly call it. And we could also refactor this down and make it look a little bit more elegant. But first, let me show you something. This is a tuple that I'm going to create of int and string. You know already that this will work, but I'm going to change things up. I'm going to tell you that when we call an arrow on any object, arrow is a part of any. And what this is going to do is convert this arrow 3 into a tuple. So it's going to convert this into a tuple with the number 3 and the string 3. This is a tuple. And in fact, let's go ahead and print that out so that way we could verify that. Great. Now let's go ahead, compile it, and run it at the command line. Okay, so let's compile maps and let's run it. We see that this is a tuple, number 3 and the string 3, T-H-R-E-E. It creates a tuple 2. Let's go back. Since we know that this creates a tuple 2, what we could do is we could then create the map like the following. Instead of all these parentheses, we can make it look a lot less lispy and more like Scala. Of course, I'm just kidding. We love the lispers. All right, 1 to the string 1, 2 to the string 2, and then 3 to the string 3. Again, arrow just converts these to tuples. That's all we're doing. And there we go. M, M2, M3 are all the same thing. Line number 8 probably has the most syntax sugar, but it looks nice, easy to read. Let's try retrieving some information from these maps. So we know that if we have a map, we can get the information by calling get. So if we call get1, this is going to return a sum of 1. What is that sum? Well, we already recognize it as an option. And if we call apply 1, what we're going to get is the direct answer. But you can kind of tell this will likely be very dangerous. Now, print line M3, and in this example, let's try get for something that isn't there. We know there isn't a for key along with this, and this will return none. Get is safer, obviously, because we're returning an option. Whereas apply, and again, the thing about apply, we don't have to call it. Calling apply is a little bit more dangerous, and this will result in an error. Okay, so what should we expect from this round of running? Well, we should expect a sum of 1 as a string. We call apply, we should just expect a string of 1. Both line 11 and line 12 are the same thing. Line 13, if we call get, then we'll get none because there is no for key. We'll not be able to find that. And if we call m3.apply or just m3 and for as the key, then we'll receive an error because it does not exist. Go ahead and save it and verify. Our blow up right here, no such element exception, key not found for. But for the rest of it, here it is. Sum of 1, and here's 1. These two are the same. These are the apply. And this is getting something that isn't there using get. And this is what happens when we call apply for something that isn't there. Obviously, we don't like this exception. Let's go back to our code. We'd rather do a get because that returns an option. It's safer. You may have some other reason in the future to use apply, but for the most part, I think you'll be very satisfied with get. Let's try something else. For a lot of these collections, you could call to and whatever collection you want to. So what I'm going to call here is to list. And what this is going to do for me is it's going to convert this map into a list. Let's give that a try. And there it is. What's fascinating about this is that it reveals what is actually going on internally inside of a map. Inside of a map, it's just holding a sequence of tuples. When we call toList, all we're going to get back is the list of those particular tuples. Pretty nice. If I ever want that list, I could just call toList, or I could call toSet. Let's go back. If I want the keys, I can call keys. Probably is not going to display too much since this is going to return an iterable. Let's try it anyway. So we'll go ahead and save that. And let's take a look. It returned a set. Pretty nice. Because there's another one called keySet. Let's go back. So I was wrong about the iterable. This does return a set. And keySet should return a set as well. Let's see what the difference is between these two. Fair enough, they're both sets. Now let's take a look at the values. We could retrieve the values just by calling values. Let's take a look at the API. So under the trait right here, there's a method called values. And this needs to return an iterable of b. But in all likelihood, we could end up with the same thing where we end up with a set. So let's give that a try. Go ahead and save that. Let's go to our command line. This returns something called map-like. Just another structure, but we have the same methods that we could use. If we don't like this map-like, in all likelihood, there may be a toSet. That way you can convert that to a set. Remember, you could call this to and whatever collection you want to change it to. If you want to change it to a list, you can use a list, whatever it is you'd like. Let's go back. And there it is. There are the list of values. Now let's create a different kind of table, this time using symbols as keys. So let's talk about symbols first. Let's go back to our code. As far as a symbol is concerned, a symbol is like a string, except everything is what's called interned. One symbol is always equal to one another. That is, if they are indeed the same. And this is perfect for keys. Now, what is interned? Well, let me show you this. Let's say I'm creating a new string, and for this one, I am just directly stating literally that I want to create a string. So is s equal to s2? The answer for that is going to be true. Remember, double equals means check for the business methods to make sure they are equal. That they are. But if we ask, is s pointing to the same object, that will be false. Because we're instantiating this, and this string right here is what's called interned. Think of it like a swimming pool for strings. And every time we literally declare a string like this, then what it's going to do is it's going to check the pool first, see if there's a string already there, and if so, we're just going to refer to it. But it's hard to track strings as keys because sometimes they're interned, sometimes they're not. Let's go ahead and run this, save it, we'll compile it, and run it. We get a true and we get a false. Let's go back to our code. Now, what about a symbol? Let me add a few lines here. What makes a symbol so great is that we could do the following. We can call symbol. Let's go to the API, take a look real quick. Here we are at the API, and I'm going to take a look at the companion object, and we have an apply. All we have to do is give it a string, and we get a symbol out of it. Let's go back to our code. So we could either create a symbol this way, or we could create a symbol with a tick mark and then the content. Either way, it works just fine. What's great about symbols? Everything is interned, meaning that this is going to be true. However you create a symbol, it's going to have a pool onto its own and make sure that everything is equal. And of course, are pointing to the same object. So both of these will be true. We'll go ahead and save that. Now let's go to the command line and verify. true and true. So symbols are perfect for maps, especially for the keys. Now, let's create a map with symbols. Let's create our own small periodic table of elements, and if we want to, we could declare that this map is going to be a map of symbols and their names. We can create that with the symbol and the string. And this is us retrieving a value with a key, that key being a symbol. Let's save it. Now let's give it a try. We get some cobalt. Looks great. Maps are table-like collections that store keys and values. Internally, maps are a collection of tuples and can be operated on as such. Symbols are like strings but are guaranteed to be interned, and this makes it perfect for maps, particularly keys. Arrays are an essential part of any JVM language. In fact, when we use this collection, it turns into a primitive array when compiled. And when we talk about a primitive array, we're talking about the arrays that the original JVM understood. For the most part, from the Scala perspective, we can interact with this pure Java array the same as we do with a list. One of the other big differences, though, is that an array is mutable, just like the primitive arrays in Java. Let's play around with arrays. I'm going to create a file called arrays.scala. And what you're going to find for the most part is that everything that you are used to when it comes to a list applies to an array. And this was actually a big deal when it was designed, because as of 2.8, they didn't get it just right. So there were a few things that were insurmountable at the time, but they overcame it. Now, what's great about this is we could just treat arrays like we treat lists. And that's a great thing. Let's get started. Arrays.scala, let's go. All right, so here we are under arrays.scala. And what I'd like to do is create object arrays extends app. So now that we have something runnable, let's get started. First one, I'd like to create an array. I'll be explicit about it for this one. And I'm just going to create an array of 1, 2, 3, 4. And what this looks like under the underlying JVM, it just looks like a primitive int array. But we don't have to treat it like that. We treat it just like any other collection in Scala. And that's what's really one of the great things about Scala. And like I mentioned, we could do all the things that a list does. We could ask for the head. We could ask for the tail. We mentioned init and last. If we want to get an element, say we want to get, let's try something a little bit more reasonable. Let's take the last one. Let's try 2. Again, this is an apply. And just like the list, we could find things like the max. We could ask it if it's empty, and so on. Let's give all this a try. We'll go ahead and save all that. And let's go to the command line. Now, just a tiny bit different. The first one is the head, so we got 1. Tail, well, that's an array. That's why we see it like this. We called a init. Remember, a init are the first elements minus the last one. That's just an array. Last one is a 4. We grabbed an element using apply. We called max, and we also called isEmpty to ask whether this is empty. Back to our code. So all that worked. Now, where arrays are used extensively in Scala are as a repeated parameter. Repeated parameters in Scala also allows us to accept more than a fixed number of parameters. Again, it's arrays that are going to drive all this. Let's get started with another example. I'm going to create a method, and I'm going to use repeated parameter method. That'll be the name of our method. And we will receive an int, we'll receive a string, and we will receive, and we've seen the signature before when we created our list, we will receive anything else with a star. Now, one thing that we could do, let's say D, and we'll use a string format for this, and we'll say give you %s, and what we're going to do is we're going to format this with whatever x is, whatever y is. Once z comes in here, in fact, just so that way we can see what's going on, let's print this out. But what this is going to be is it's going to be what's called a wrapped array. It's essentially an array. Wrapped array is nice because it has a nice 2 strings so we could actually see what's in it. Within here, what I'd like to do is state z makes string. We know what make string is. And let's just say that we want to comma delimit all that. Okay, so we have to give it an int, we have to give it a string, and then z is optional. We can leave it out, or we can have 1 item, or we could have 10 items, or 20, or 50. Because that's what's called a repeated parameter. So how do we use this? Well, let's try one call, and then we'll run it. I'm going to call repeated parameter method, and I'm going to say 3 eggs will make, well, for 1, it'll make a delicious sandwich. it'll give us protein. And who knows about this one? Some doctors say yes, some doctors say no. But we'll just say this has high cholesterol. What is this going to look like? Here's our int. Here's the one string that we want. And this right here is going to be placed in as our var args. So let's give it a try. Let's go ahead and save that. And let's go ahead and run it. Okay, we see that this is a wrapped array, a delicious sandwich, protein, and high cholesterol. That was the print line we had. So let's go back. Now let's see what this is. I'm going to wrap this whole thing up in a print line. And the end result is, let's go ahead and save it. Now go to the command line. Great, looks good. 3 eggs give you a delicious sandwich, protein, and high cholesterol. Let's go back. If the last part is a wrapped array, what happens if we do this? What happens if we give it a list? I mean, it's just a collection, right? That should work. Let's save it and let's run it. What's happening here is that we have a wrapped array of a list, and it's one single item. Now it says right here, 3 eggs give you list, a delicious sandwich, protein, and high cholesterol. But we don't like that list there. I mean, it looks kind of ugly. So one of the things that we could do, let's go back, is right here we can add the following. And this is just syntax sugar here. We could state right here, colon, and what this is going to do is it's going to break it apart. This list or any other type of collection is going to break it apart so that way it could fit into this repeated parameter. Let's save that, and now let's give it a try. Now, what this does is now a list, and now we could say 3 eggs gives you a delicious sandwich, protein, and high cholesterol. Works out pretty nice. Let's go back to the code and take a look. Again, this is a repeated parameter. Arrays in Scala are converted into primitives arrays on the underlying JVM. Behavior-wise in Scala, they are similar to lists, but arrays are mutable, so be careful. Perhaps what you could do is you can convert that into an immutable collection after your use. Repeatable parameters use an array, a wrapped array, to hold the possible extra information. In this session, we're going to talk about ranges. Ranges are a way to create a collection as a range of items, rather than one by one. Let's start with a file called ranges.scala. Let's give it a whirl. Here's ranges.scala. Let's go ahead and get started. Ranges are extremely simple to set up. So instead of doing 1, 2, 3, 4, let's say I want to go all the way to 10. Well, I don't have to go through all that. All I have to do is just do 1 to 10, and that will create a range for me. Or I could do 1 until 10. This one will include the 10, and this one will exclude the 10. And these are collections. I could do just about everything that I could do with a list with a range. For example, if I wanted to call head or tail on R2, I could do so. Let's save this and let's give it a try. Here, the top one is 1 to 10. Second one is 1 until 10. Again, does not include the 10. Second to the last item is the head. And then we have the tail. So all the same methods as we have with list we can use with ranges. You could also create a range by step. Let's go back. We could do something like this. Let's do 2 to 10 by 2. That should be easy to see what happens. 2, 4, 6, 8, 10. Let's try it. Looks really nice. We could also go in reverse. Let's try that. Let's go to the command line. Looks great. Now characters are integers as well. So that means we could do something like this. Let's go back and give this a try. Ooh, this ought to be a lot of fun. Let's print out our 5. Let's see what happens. We have a range. This just happens to be called numeric range, but it's still a range, and we could still operate on it just like any other range. A, B, C, D, E, F, G, all the way up to Z. In fact, we could do the following. We could take this, and remember, plus plus concatenates 2 lists or ranges together. Nice. So let's save that, and let's see what we get. It's a different structure, but it's kind of like a list. It's called a vector, A, B, C, D, and we have our capital letters. Now, whatever we get returned is not always going to be exact, like we're not always going to get a range in return, but what we're going to get is something with the same characteristics. And since we have a clean API in Scala, we know that we could call head, we could call tail, we can call any of the methods like map, FlatMap, etc. that we'll be talking about later. So that worked out really well. Now, we could also create ranges explicitly by using the companion object for range. Let's give that a try. Let's head back to our code. All these were wonderful syntactical, sugary ways of creating ranges. but we can use apply. These are exclusive. We'll save this range. Let's give that a try. Does not include the 10. Again, by default, they are exclusive. Does not include the last item. Let's go back. So again, all we're calling here is the apply method. We could do this with a step. 1, 3, 5, 7, 9. Looks good. Now, if we want inclusivity with our range, we could do that. Let's go back. This would be exactly like 1 to 10. And here's 1 to 10 with a step of 2. Or that wouldn't make that much sense. Let's change that to 2. And then we'll add the print line. Let's take a look at these ranges that we created using range inclusive. There it is. Range inclusive 1, 10. That's the second to the last one. And range inclusive 1, 10, 2 will create for us 2, 4, 6, 8, 10. In the end, worth stressing again, just consider all the methods that you can run with range the same as you could run with a list. Of course, you could always convert this range to whatever collection you want by calling to and whatever type of collection you want, like toList, toSet, etc. Now, ranges are going to play a dominant role for for loops and for comprehensions. Let's try out a for loop. For example, if I have 4, I can do 1 to 10. And this is a typical scenario, but that 1 to 10, as you know now, is a range. Now, just for information's sake, I could have done 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but that's too much. 1 to 10 is very handy. Try a couple scenarios. How about 1 to 10, and how about 2 to 10 by 2? Let's save that. In fact, we can put a divider here so we know which one is what. And there we go. So the first one, we should have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And the second one should be a tough one. 3, 5, 7, 9, and 11. All right, let's see if I'm right. So I'm going to go ahead and save ranges.scala. Now let's run it. Okay, there we have it, 2, 3, 4, all the way down to 11. And for our second one, hooray, I was right. 3, 5, 7, 9, and 11. And those are ranges. Let's go back to the code and review. 2 different ways to create them. I could either do the companion object, or I could use syntactical sugar by calling something to something by something else. Ranges are a way to create a collection of numbers or characters without specifying them one by one. We could treat ranges with the same methods as you would a list. You can create ranges with syntactical sugar, again by using 1 to 10, for example, or you could use any of the factories in the range companion object. In this session, we finally get to start learning some basic functional operations. One of the most fundamental operations in any functional programming language is map. It takes a value from a container and applies a function to that value, or those values, and returns a new container with those manipulated values. So let's start off with a list in a file we'll call mapfunction.scala, and we'll play around with this operation called map. Here we are in mapfunction.scala, and we're going to start off with an object that extends app that we can run. Here's our object. I'm going to create a list, and I'm going to create a function. Excellent. So for the list, I could have done 1 to 6 and created a range, but this works just as well. And for the function, I have a function that will be brought in an int, and given that int, we will add 1 to it and return that result. The type is going to be an int to an int. So at this point, let's take a look at the API for list, and we're going to look at the operation called map, or the method called map. Okay, and here we are looking at the Scala API. We have final def map. Final meaning that any subclass cannot override that. Def, this is a method, map, and then parameterized type B. Now the list that this method is contained within has a parameterized type of A. So if we have a list of int, then A is of a type int. By operating on this map, whatever the return type for this function is going to define what the parameterized type B is. So if we give it a function from int to string, then parameterized type B is going to be a string. The end result is going to be a list of B. That's map. And as stated right here, builds a new collection by applying a function to all the elements of this list. Let's go back to our code and give it a try. So given this now, what I'd like to do is do the following. Excellent. So given a list with A, I'm going to call map and provide it with that function. I'm going to go ahead and save this And let's compile and run it, see what happens. Great. So we have a function that adds 1 to every element of the list. We started off with 1 through 6, and now we have 2 through 7. Excellent. Let's try inlining that function. So that function that we created was on the outside, but what we can do is call map with a inline function. So let's go back to the source code and give that a try. I start off with a.map, but this time what I'd like to do is create a function inline. So I have a.map, and I'm going to provide an inline function. This function says, if you give me an int, take that int and add 1. So this should be the same. I'll go ahead and save that. Let's compile and run again. And there it is. It looks the same. So we've already had some experience with getting rid of some explicit types and allowing the compiler to use type inference. Let's go back and add a different variant of this map by taking away the type. In other words, this type was unnecessary. The reason? This list is already of a type list of int. Therefore, x is already going to be established as an int. Let's go ahead and save that, and we'll go to the command line, compile and run. There we go. Now remember the placeholder. If I don't want to come up with a variable or a value name like x, I could replace it with an underscore. Let's go back and give that a try. Great. Let's compile and run. It looks great. Now remember, addition is commutative, so we could flip that around if we need to. Let's do that. So this could be 1 and this could be underscore. I won't bother running this one. We know that's going to be the same. But remember the rule, if we have an underscore at the end, we can get rid of that. Let me bring this one back just so that way we have this available just to show the history. Now let's compile and run. We are going to see a warning. This says there's one feature warning, rerun with dash feature for details. Do that. There we go. This says warning, postfix operator plus should be enabled by making the implicit value scala.language.postfixops visible. This could be achieved by adding the import clause import scala.language.postfixops. Great, tells us what to do. Let's go back. So this is just a feature flag. If we want to use a particular feature, a particular advanced feature, we just need to include that as an import statement. So let's go ahead and include that. Import scala.language.postfixops. Now we'll compile and run, and we should have the same answer. Now they all are. That looks great. But just as we can do with a list, we can do with a set. So now let's use map with a set. Let's go back to our code. Now I'm going to create a set, and this is going to be a set of string with colors. Our colors are brown, red, green, purple, gray, and yellow. What I would like to do is I would like to use map to take each element and return the size. Now, this is a different function. We are bringing in a string, and we are returning an int. It's going to be a little bit different than what we had before. Before we had an int coming in, int coming out. This one has two different types. First one is the string that's coming in, and as far as the function, this is an int that's being returned. Why is this important? Well, for the map function that we did with the list, that was an int coming in, int coming out. That meant that we started with a list of int, and we ended with a list of int. But this time we have a set of string, and since we're applying a function that takes a string and returns an int, we're going to be left with a set of int. We went ahead and saved this. Let's compile and run. Now we have 6, 4, 3, 5. But we had 6 elements to begin with. What happened to 2 of them? Let's go back to the code. What happened is that some of these strings happen to have the same size. And for sets, they could only contain unique values. Brown and green have 5, purple and yellow have 6. We can have no duplicates. That's why we ended up with 4. But now let's take this line and simplify it. Obviously, we didn't need to name anything x. We could have just used underscore. Now, let's compile and run. 6, 4, 3, 5. Same thing. Now let's try something fun. Let's say we want to retain the color and the size of that color string inside of a tuple. Let's go back. So this time I'd like to call bmap. For every string coming in, I would like to return a tuple of the original string that came in and the size of that string. Let's go ahead and save that and compile and run. Great, we have green 5, brown 5, gray 4, red 3, yellow 6, and purple 6. That's pretty neat. You can use the map function on anything. Now what I'd like to do is try it with maps, and this time we're going to use the Men's World Cup Championships for this example. And remember, before we begin, maps, if you recall, are just collections of tuples. Let's go back to the code. I'm going to create a value called FIFA Men's Champs, and I'm going to create a map. And given this map now, what I'm going to do is create the team called Germany. They have 4 wins. And this is the key. We'll be using a symbol. Next, Brazil. They have 5 wins. Next, we have Italy. They have 4 wins. And then finally, Argentina, which has 2. Looks great. Now, let's say for every key, I want the name, instead of Germany, Brazil, Italy, and Argentina, I want the name to be Team Germany, Team Brazil, Team Italy, and Team Argentina. Now, these are symbols, these aren't strings. So we're going to have to look into the API and see what calls we can make. But we got to start somewhere. So print line, FIFA Men's Champs map, and for every tuple that we're getting in, this is a function, what I'd like to do is I would like to call this Team Germany, Team Brazil, etc. And this has to be a tuple. So we'll go and get started here. We know we need a tuple. And I know that I still want these wins to stay the same. So I'll leave that one as T2. But this right here, I need to know what I'd like to put in here. Let's do some research. We know that if I bring in T1, that this is a symbol. But what I want out of here is I want the name that is associated with the symbol, and then learn how to create another symbol in its replacement. So let's head over to the API. For symbol, this is what backs up the symbols. And as far as the class is concerned, we only have equals hashcode name. That's the one we want to extract the name, and toString. So how do we create it? Well, I don't see any constructors in here. So let's take a look at the companion object. Maybe there's a factory we could use. And there it is, our friend apply. We use apply to create a new symbol, and we call name to extract the name out of a previously created symbol. Given all this information, let's head back and solve our problem. So T1 is going to represent a symbol. If I want the name out of here, here's the name. If I want the word team, here's team, and I'm going to add the name. To create a new symbol, once again, I'm going to call symbol.apply. And finally, one more paren. Okay, I think everything should work. So let's go ahead and save that, and let's compile and run. Great. Map, and it says Team Germany has 4, Team Brazil, Team Italy, and Team Argentina. That was thrilling. So how about this? Let's go back to the code. We tried that with a map. We could also try this. In fact, we don't need a val. We could just say printline hello.map and then add 1 to each character. Now I suspect that with this is going to return a collection of integers, because characters are integers, so that's what I'm expecting here. Let's go ahead and save this, compile, and run. So this is a vector 73, 102, 109, 109, 112, and 34. Not quite what we wanted, so let's go back and fix it. What I'd like to establish here is that even though these are numbers, I'd like to make these into a character. We'll save that. Now we will compile and run. There we go. At the end here, I have capital I, small f, MMP, and a quote, which if you think about it, we had hello with an exclamation point with a capital H. Therefore, the next letter is a capital I. E, next letter is F. For L, next letter is M. Therefore, we have 2 M's. And O, next letter is P. Is it useful in real life? Maybe not. But this just shows you that strings can also be mapped. Options are also mappable. Let's give that a try. Let's say we have a sum of 4. And what I'd like to do is to map that we add 1 to that 4. Options really a container. The sum is a container. This is going to contain a 4. And if we map to it, then we should end up with a sum of 5. Let's compile and run. Great, we have sum of 5. But be careful what happens if we do the following. Let's head back. Something dangerous is going to happen here, but let's try it out. This says ambiguous reference to overloaded definition. Didn't know what to do with this. We had a none, but right here, there's no guidance as to what type we are using. And currently it thinks that we're using an option of nothing. And we can't really add anything to nothing, and so it's a little bit confused as to what to do. We could do a couple of things to make this work. In particular, we can call as instance of to convert that none to an option int. So let's give that a try. Now this will recognize this as none, but as something that should have been known as an option of int. Let's go ahead and save this. Let's compile and run. Looks good. Now, another thing we could do is we could have made this an assignment. But since we're clear that this is an option int, and if we try to do a map on something that is none, that in turn should be none. Theoretically, that should make sense. Okay, so let's try the assignment I was talking about. Let's go back to our code. Now, to establish that this was an option int, we could have done so by doing something like this. That should work out as well. Let's compile and run. Great, we get none. Everything worked out great. Everything makes sense. Well, you can map over a none. You're just going to get none in return. And it should make sense that we do get none. So in conclusion, map takes a function and applies that function to every element in that collection, whether it be a list, a set, a map, streams, strings. It can also be applied to options. Another method of importance is filter. Filter retains items that match a predicate. A predicate is a function that returns a Boolean. Let's try out filter. We'll try out its mortal enemy, filter not, and we'll try exists. Let's create a file called filterfunction.scala and try these elements out. Let's get started. I'm going to start off with a range with a 1 to 10, and let's try out filter. And what I want to do in this case is I want to filter out all the even numbers. This is a predicate. Remember, a predicate is something that is a function that we will return a Boolean. This is a Boolean, therefore it's a predicate. Let's go ahead and save that, and let's go ahead and compile and run it. And there we go. We're able to filter out all the even numbers. Works really well. Filter not is the opposite. So let's go back. And by placing a filter not here, this is now going to filter out all the odd numbers. We want to filter the things that are not even, is what we're stating here. We'll save it. Now let's compile and run it. There we go. We get the odd numbers. Now exists will ask whether or not there are any even or odd numbers, however you want to do it. Exists will take a function, and it will use that function to determine if any one of the elements meets that particular function or predicate. It has to be a predicate, something that returns a Boolean. Let's give it a try. Now, we saw what contains did. Contains asks, is this certain element in here? This one will ask, does this function apply to anything in here? Two different things. Let's go ahead and save that, and let's give it a try. Answer is true. Obviously, we have some even numbers inside of this range. Of course, we could clean up how we invoked all this. For all of these, we did not need all this extra stuff here. We could have used the placeholder. Very simple. We did this with a list of numbers or a range. But we could do this with strings. Let's get a little crazy here. What I'd like to do, let's create a method called filter vowels. And given a string, let's first convert everything to lowercase. To lowercase happens to be a method on string that converts everything to a lowercase. And what I want to do is I want to filter out everything that happens to be a vowel. Now, typically I would use a regular expression for this, but I'm just going to use plain Scala for this particular solution. We've built up our knowledge to everything up to this point. We're using characters, we're using a set, and we are asking in this set, does the character that we are talking about contained inside of the set A, E, I, O, and U? This is filter on a string. So before we had a list of numbers, now we're using it with a string. Let's give this a try. Let's see how many vowels are inside of orange. Let's save it. Now let us compile and run it. Orange has 3 vowels, O, A, and E. That was really nifty, but we could also use filter with a set. No problem. So we've used filter with a list of numbers. We've used filter with a string. So now let's use this with a set of string. We won't get too deep. It's exactly the same. But with it, let's do something clever. Now let's say we are going to create a set, and we'll use our set of colors once again. Red, blue, green, purple, and orange. What do I want to do with this? Well, let's do a print line, and let's take this set, and let's filter out all the strings that have colors whose number of characters, and these are the vowels we're talking about, are greater than 1. Let's state that again. I have a list of colors. Each of these colors have vowels. What I want to do is I want to filter out the colors that have vowels greater than 1, or the size of the vowels greater than 1. Red has 1 vowel. That won't meet our predicate. Blue has 2, so that will meet our predicate. Green has 2, that'll meet our predicate, and so on. We're going to filter out the vowels. We're going to take the size of the vowels. And if the size of the vowels is greater than 1, then we want that included in our list. And it's actually very easy. So I'm going to call b.filter, and then for every string that's coming in, we already implemented this. I want to filter out the vowels that are in here. take the size of it and ask if it is greater than 1. And that's it. We're actually using 2 filters because filter vals has a filter of its own. Let's give this a try. Very nice. We don't have red there, but we have blue, green, purple, and orange. Very clever. Can we use this for maps? Of course we can. Let's try a filter with a map. And let's add 4. All right, so there's our map. Our keys are ints, our values are strings. Now, let's use filtering. I'm going to take this map and I'm going to filter the keys. And I want only the keys that are even. So we'll go ahead and save that. And now let's give this a try. Wow, that was really impressive. So what we were able to do is filter out elements inside of a map by the key. And if the key wasn't even, then we remove that. That's very powerful. Now let's go for some other goodness. What if we have a sum of 5 and we wish to filter this? And what we'd like to do is filter it if it is an even number. In fact, let's do both of them. Let's do one that has 5 and one that has 4. Let's see what happens with this. What we're doing again is we're taking sum 5, that's an option type, and we're going to filter that with a function. Second one, we have sum 4, and we're going to filter that with a function. The function is, this has to be an even number. That's our predicate. Let's save that. Wow. So the second to the last item is none, and the last item is sum of 4. Very, very interesting. Let's go back to the code. Why was this one none? Well, we had sum of 5, and then we filtered it. Since it could not meet the predicate, this is now a none. And here's sum of 4. We filtered that. 4 is even, so we retained it. How awesome is Scala? So filter filters out elements that meets a predicate's criteria. Filter not filters out elements that does not meet a predicate's criteria. Exists tests if something exists in a collection based on a function. Filter, filter not, and exists are all available for lists, ranges, sets, maps, options, and on and on and on. It's all about having that clean API. In this session, we discover the ForEach method. ForEach method is a method that almost looks like a map and acts like a map, but instead of giving it a function that returns another element, we need to give it a function that returns unit. You remember unit? The reason for this is to perform a side effect with each iteration. Without it, we'd be left with a map, and map returns something. But for functions that return unit, this could be a little bit messy. So let's consider the following. Let's head over to a file called ForEach. What we'll do is we'll create an object called ForEach that extends app. That way we can run it. And let's say we're going to start off with a range 1 to 10. And what I'd like to do is print out what a.map, and what we'll do is we'll take each item and print it out. So printline is a perfect candidate because this returns unit. Printline is a side effect, meaning that something is being printed to the screen, then nothing else. We don't get any evidence back. Something that happens out of our control. Let's go and save this, and let's take a look at what the end result is. Here we are at the terminal, and I'm just going to do Scala C. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but we got this problem. It's not really too much of a big problem, but what we got in return is all these units. So we're able to printline every item, but we get all these units at the end since this is a map. And remember, map has to return something. It'll be nice for this just to return unit from here. And that's where ForEach comes from. The only thing is that each item is given a function that returns a unit. Let's take a look at the Scala API. Here we are at the Scala API. This is list. We could also pull up range if we wanted to. But what we want to look at is ForEach. And here's ForEach. This is a final def ForEach. We're giving it a function. The function is going to take in an A and return a unit. Again, something like this is perfect with println. And it's going to return a unit. Map is a little bit different. Map says take in an A and return a B. Well, in our previous example, B was a unit. And what it ended up making was a list of units. That's why you saw the open paren, close paren, open paren, close paren, as you did before. But ForEach is going to just return a unit. And it's perfect for that sort of thing, because we're not expecting anything in return. Let's change our map to ForEach. Here's ForEach, and let's see what we end up with. Let's go to the terminal. Great. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we get a unit in return. We don't get a vector of a bunch of different units. That's great. Now let's go to the code and do some cleanup. So we don't need this print line. We know now that we're not returning a vector of units. That looks good. And also, we could get rid of this X here and replace this X with an underscore. Of course, now, since there's only one argument, we can make this println underscore. Now, there's only one argument here, so we could just say A for each and println. But what did we say about the underscore? If it ends in an underscore inside of a method parameter, we could just get rid of that underscore. These parentheses are useless, so now we could just do A for each println. Let's go ahead and save this, and let's take a look at the result. Beautiful. Now I think you're getting the point, so I don't have to do this for all the other collections. ForEach is a method that could be applied to sets, strings, streams, ranges, arrays, what have you. Now ForEach is a method that takes a function, and that function takes each element and returns a unit. This is perfect if you want to take an element and perform a side effect like print to the screen. Of course, ForEach is available for lists, ranges, sets, maps, options, whatever you'd like. One of the trickier topics is FlatMap. Mystery shrouds this method. So let's take a look at code right away. That way we get a better understanding. I'm here inside of a file called flatmap.scala. So let's go ahead and create that. And within this file, I am going to start off with an object that extends app. And in here, we're going to start off with a list. Now that we have this list, let's get going with a map. And for every element I'd like to bring in, I'd like to create a list. I'm going to go ahead and save that, and I'm going to compile and run. Okay, this was to be expected, a list of a list. Because for every element, so if we start off with 1, and we're going to create a list of -1, 0, and 1. Next one would be a 2, therefore -2, 0, and 2, and etc. Now this is just a plain map, and it did return a list of a list. But let's say, given all that, what we want to do is take this and flatten it. This is where the flatten method comes in. So let's head back to our code. I'm going to add flatten. In fact, let's do this a little bit at a time, so that way we have a record of this. I'm going to add flatten. Let's compare the two. There we go. The one on top is map. The one on the bottom is map with flatten. Let's go back to the code. Now we have flatten and map, flatten and map, flatten, map. This really is FlatMap. So if I made this into FlatMap, we should expect the same thing. Let's compile and run. Same thing. And it works out great. So we see that we no longer have a list of a list. We have a single list. And so if you want to make a mental note about this, and you may find this helpful, if you see a collection of a collection, like a list of a list, set of a set, map of a map, a stream of a stream, etc., like we just saw right now, and you don't want it like that, now, there's nothing wrong with having a list of a list. But if that's not what you're after, then FlatMap is going to be your tool. Now let's go to the API and let's take a look at the method call to see how we should actually work with this particular method. Here we are with the API. Let's take a look at the list implementation of FlatMap. This is a final def FlatMap with a parameterized type of B. It almost looks very much like map. The only difference is the function. If we give it an A, this returns a general traversable once. What is this general traversable once? Well, this just happens to be a trait, and again, a trait is very much like an interface in Java. And this has many subclasses. And take a look at all the different subclasses that are available. It has a lot of varying collections that we can use. Let's go back and let's take a look at FlatMap again. The function is, it takes an A, and we have to return some sort of collection, something that is of a type general traversable once, of the parameterized type B. And that in turn will return a list of B. So let's take this example, and what we're going to do next is we're going to create a collection that is multi-layers deep, a list of a list of a list, and see what happens. Let's go back to the code. As I stated, I want to create a list of a list of a list, and this one will have a 1, 2, 3 to it, and this one will have another list of 4, 5, 6, and that would be the end of that list. Then we'll create another list of list in the here. What we'll have is a 7, 8, 9, and a list of 10, 11, and 12. Great. So let's save that, and let's do a compile to make sure everything is accurate up to this point. Everything looks good. But let's go back to the code, and let's put in the explicit type. That way we can know what we're dealing with. B is of a type, a list of a list of a list of type int. And we have that multi-layers D. Now this looks like madness, but this is always achievable depending on your calculation and what you derive to. And it could just very well be that during your regular programming that you'd end up with a list of a list, or a list of a list of a list, or a set of a set of a set. So don't be surprised when you're faced with this scenario. What is the result of performing a flat map on a list of a list of a list of int? Well, that depends on your function. But if we provided something like an identity function, then that function will shrink to a list of int. Now, I haven't described what an identity function is yet. Identity function is a function that takes an argument and then just returns immediately that same argument. Let's give that a try. So given this list, what I'd like to do is I'd like to call println, take that list, call FlatMap, and provide it the identity function. I use C here to take the place of collection. It could be an I, it could be an X. I just chose C. Let's save this, and let's compile and run. Now, we went from a list of a list of a list of int to a list of a list. We went down one level. What happens if we call FlatMap again? Since we have a list of a list, we can do this. We'll save it. Let's compile and run. Great. So what did we end up with? We ended up with a list from 1 through 12. And we're down to a list of single items, a list of int. What happens if we do it again? Well, let's make that mistake. Now remember, after this point right here, this call is meaningless. We already had before this a list of int. By calling FlatMap again, taking a C is not going to cause it to be returning a collection or a general traversable once. But let's go ahead and save that, and let's make our mistake. I'm going to head over to the terminal, and compiling should fail. And this says it found an int, which is true because we are bringing in an int, and what it was expecting was a general traversable once, but it was an int. So that didn't work. So again, let's take a look at the Scala doc. Here's the Scala doc. We were expecting a general traversable once, but because int was coming in, we were just taking that int and trying to make this int a general traversable once, which it isn't. Int has nothing to do with general traversable once. But a list is a general traversable once, so we could do something like this. Here we are back at the code, and we could do something like this. I'm just making sure that all the parentheses are lined up. We'll go ahead and save that, and now let's compile and run. Great. So we start out with that list of a list of a list of int. We shrunk it down twice using FlatMap. And then at the end, for every integer that we had, we created a list out of it where we provided the negative number and the positive number. Of course, it flattened it, so now we have this list. Sets can be flat mapped too. Let's give that a try. I'm going to start off with a set of 2, 4, 10, and 11, and we're going to call FlatMap. For every item, we're going to take X, and we are going to create another collection. So if we have 2, we're going to create another set of 2 and 10. If we have 4, we're going to create a set of 4 and 20, etc. And then what we'll have is a set of a set, but since it's a flat map, everything will be flattened. I'm going to go ahead and save that, and let's go to the terminal, compile and run. 10, 20, 2, 50, 11, 55, and 4. What's really fascinating is that we are applying flat map to a collection that has certain rules. Set has certain rules in this case, and they must have unique items. Therefore, 2 times 5 is 10, but 10 is already in the set, so it wouldn't be necessary to include that after the flat map. 20 will be included, 50 and 55 since they are unique. Pretty cool. Now let's try maps. Maps can be flat mapped as well with some pretty interesting effects, so let's give that a try. Let's head back over to the code. First, we'll start off with an original map, and this map will start off with the number 1 as a key, and the string 1 as a value, number 2 as a number, then 2 as a string, TWO, and to round things off, 3 and 3. Now let's have some fun. Print line, I want to take the original map, and I'm going to call FlatMap. Now every map is a collection of tuples, so this should be a tuple coming in. And given this now, this should be some sort of collection. So let's make that a map. And what is this a map of? Well, for each entry that I have, I would like to create the following. I'd like to keep T1 as the key for this entry, and T2, keep that normal. But for the second one, what I'd like to do is I would like to take that T1 and multiply it by 100. And for the value, I would like to take T2 and then add the string 100. That's the map, that's the flat map, and then there's the end for the print line. Great. I have original map, flat map. For every entry, I'm going to create a map with 2 entries. The first one is going to be the normal one with the T1 and the T2. The second one is going to take the key, multiply it by 100, take the value, and append the string 100 to the end. Pretty exciting. Let's go ahead and save that. And let's go over to the terminal, compile and run. So I have 1 and 1, 2 and 2, 3 and 3, but because I did a flat map, I now have 300 with the value string called 300. 200 now has a value of 200. 100 has the value of the string of 100. That is really cool. Now options are flat mappable too, and they're fun to flat map. So first, let's create a perfect scenario using a sum with a value that will map first, and then we'll try some harder conditions. We'll start off with a sum of 4, meaning we have some sort of answer, and we'll call map, and for every item that's coming in, we are going to return sum, given that number, plus 19. We're starting off with a map first. Let's see what ends up happening. Let's go over to the terminal. We have a sum of sum 23. And just like I stated before, whenever we see a collection or a container, a sum of sum, a list of lists, map of map, that's our call to flat map. Not that we have to, depends on your need. If you see something like that and you don't want it, then use a flat map. Let's head back to our code and change this to flat map. Let's save this. Now we have a sum of 23. That's pretty amazing. Now, as a difficult condition, what if this started out with none and we try to flat map that? Let's make our terrible mistake first and then fix it. Our terrible mistake would be starting off with a none, doing a flat map. For the element that is inside, which there isn't, we are going to return a sum of x plus 19. Now, let's go ahead and compile this, and let's see the confusion that the compiler is going to display. Okay, this says right here that value plus is not a member of nothing. What's happening here? Well, none, the none that we see here, by default is going to be of a type option of nothing. So what we're doing is we're calling flat map. Therefore, the x that is coming in is not of a type of anything that we know really except nothing. X, its type is nothing. So what we're doing right where that little caret is right there is we're taking nothing and adding 19. That's a bad thing. What we would need to do is we would need to specify that none is of a certain type, and in this case, a type of an option of int. Let's go back and change that. None is now an instance of option int, as it should be. Then we will call flatmap. Let's compile and run. Great. This says none. And it should make sense. Let's go back to the code. This should make sense because we're starting off with none, and then we're calling flatmap on it. And it doesn't matter what we do or what the function is. Since we started off with none, the whole thing should be none. And it is correct. Again, if you think about it, it should make sense. So let's do another twist. What if we are performing a flat map from a sum, but the function used for the flat map is going to return a none? What do we do then? In other words, we'll start off with a sum of 10. We'll call flat map. For every item, let's return none. Now let's see what we have. That too is none. And that should make sense. Even if we have an answer, even if we have a container of sum 10 or a container of 10, we call flat map on it. And within that function, we return a none. Therefore, the whole thing must be none. Let's do one last exciting example. We're going to do a print line. And this time, we're going to create a list of options. We'll start off with sum 4, none, sum 5. Let's do 2 nones and a sum of 10. Now, flat map, and we're going to use the identity function. This is exciting. So what we have is we're starting off with a list, sum of 4, none, sum of 5, 2 nones, and then a sum of 10. That's the list here. We'll call flat map, and we'll use the identity function and print the results. Compile and run. We end up with a list of 4, 5, and 10. Let's go back to the code and see what happened. We have 4, 5, and 10. So what ended up happening is that for each item, this ended up returning a sum or a none, which is a container. What happened was sum of 4 ended up returning 4. None collapsed onto itself, disappeared. Sum of 5 came in. We peeled out the 5, and that became part of the new collection. The 2 nuns disappeared. Sum of 10, the 10 got peeled out of there and became part of that new collection. What a thrill. Let's take a look at the answer again. We ended up with a list of 4, 5, and 10. And what happened is, by doing this, the nuns disappeared, and the values within the sums became just the values unto themselves and a part of that final list. FlatMap is the combination of flatten and map. FlatMap can be used with lists, sets, maps, strings, streams, and optional. Your mental cue, if you so care to use it, is whenever you see a list of a list, or a list of a list of a list, or a set of a set of a set, or a map of a map, whenever you see these kind of embedded collections and you don't want it that way, then use FlatMap. And of course, you can use it for multiple collection layers in the case of a list of a list of a list. There's something magical about the methods map, FlatMap, filter, and ForEach. What's so magical about these methods? Well, let's take a look at an idea called for comprehensions as opposed to a for loop. But first, we're going to start things off with a for loop. I'm going to create a file called forcomprehensions.scala and create an object called forComprehensonsExtendSapp. Make it something runnable so we can play around with this. Now, let's give a sample of a for loop. I'll be using a range here. I could use a list or a set. Anything would work just out fine, so I could do something like this if I want to. Or use a set, doesn't matter, but I'm going to use a range for the first example. And here I'll have a print line. So this is a standard for loop. Let's see how this looks. Here we compiled for comprehensions, and now we're running it, and we see 1 through 10. And again, this just looks like a plain for loop. But now let's create a for comprehension and compare and contrast. For the for comprehension, I'm going to first establish a result. Now the for, and now given this, I'm going to yield back I plus 1. And now we'll print line result 1. Takes on a little different look and feel. Let's run this. And we see that this is now a collection of 2, 3, 4, 5, 6, all the way up to 11. We gave it a range of 1 to 10, and we got another collection. Now this is a copy, except that every element has 1 added to it. Let's go back to the code. And when we take a look at yield, we are yielding back every item plus 1. What does this remind you of? If you remember, this looks a lot like map. In fact, they're the same. Before we continue with something else, unlike the for loop, we could assign this for comprehension to a result, a val. You could use a var, but we prefer a val. Why? Because of immutability. We want this comprehension to work so that we could assign it to a value. Now, let's compare this for comprehension to how we would call it with a map. Do a result2, 1 to 10, and call map. This would be the equivalent. In fact, just to be a little bit verbose, why don't I just do this? So 1 to 10, map, for every item, we'd like to add 1. Let's compare both of these. They look the same. Now this is what a for comprehension is for. I mentioned previously that Scala programmers rarely use for loops. We will once in a while, depending on the need, but for the most part, I think we use for comprehensions. The reason? Immutability. And when you map, you maintain the same collection type, which is a great bonus. That also means that you could plug in any object that has a map, FlatMap, filter, and a for each. In Scala functional programming, this is called Monadic. In academic circles, in type theory, our flat map is what makes this a monad. Monad is really just a flat map with many mathematical laws that it needs to adhere to. Among Scala programmers, when we say that something is monadic, that means that a particular item contains the methods map, FlatMap, filter, and for each, and can be used, of course, in a for comprehension. Now, options are monadic too. Let's try that out. So I'm going to create a val result3, and this is going to be equal to 4. I'm going to take sum 100. I is going to be that 100, and I will yield back I with 40 added to it. And this in turn should create a result of sum 140. Print out the result, save it, and let's run it. As we see, we have sum 140. Now the original 1 through 10 example is going to take up a lot more space, so I'm going to go ahead and comment that out. But down at the bottom we have sum 140, which is what we were expecting. It's still an option type, and remember we tried it before where option had a map. Same works for strings, sets, etc. And we can go back and show the map equivalent of what we're seeing here. Let's go back to the source code. So let me comment these three, so that way it doesn't take up that much space in our console. What I'd like to do is create result 4 and do the same as result 3, except use it using explicit map. Sum 100, map, and for each item, I want to add 40. Let's go ahead and print line the result. So we'll go ahead and save that, and let's compare. The same thing. Now let's go back to our code. As we see here, there isn't much difference as far as reading and understandability between the for comprehension and using a map. But these are simple cases. Once we get a little bit more complex, you may think about using for comprehensions more. This time what I'd like to do is I'd like to create a for comprehension running 2 statements within that comprehension. Let's try that. And create a result 5. I'm going to create a for comprehension here. I'm going to start off with a list of 1, 2, 3, and 4 for the I. I'm going to use a semicolon to signify that I have another series, and this will be J, list 5, 6, 7, and 8. Now we will yield I and J, and print the result. Now we're getting a little bit more complicated here. So I have I, which is going to be a list of 1 through 4. J is a list of 5 through 8. We're going to iterate through both of these. It's going to start off with 1, and then a 5, 6, 7, 8, then 2, 5, 6, 7, 8. And for every iteration, we're going to yield back a tuple of I and J. Then we'll print the result. We'll go ahead and save that. Let's compile and run. 1, 5, 1, 6, 1, 7, 1, 8. Then we go to the 2s. 2, 5, 2, 6, 2, 7, 2, 8, etc. So we take in what I and J are with each round, then produce the results. In a C, C++, or Java language environment, this looks a lot like a nested for loop. Of course, this is a comprehension, which is different, and it assigns this to a val or var. Again, we prefer a val. Let's go back, and here is the val that I'm referring to. That's what's going to be different with a for comprehension. Now, how do we duplicate this using a map? As I just stated, everything is going to be a map on the back end. Well, let's give this a try, and what we're going to do is we're going to make an error first. We start off with result 6, and for our result 6, what I'd like to do is create a list. We're not using a for, we're trying to duplicate result 5 using maps. 1, 2, 3, and 4, map. For each element of I, I'm going to bring in another list. In fact, let me bring this up all in one line. Even if I run out of space, it'll probably be clearer if I just put this all in one line. Then I'm going to map rj and then return I, comma j. Let's make sure that all the parentheses line up, and we will print out result 6. All right, we should end up with nearly the same thing again. It's almost going to look the same, but not quite. This is not going to be what we're looking for, but let's go ahead and save that and compile and run. Okay, the last two, one of them's a list and the other one's a list of a list. One's a list of 1, 5, 1, 6, 1, 7, and 1, 8. And the second one, each round has its own list, and this becomes a list of a list. What do we usually need if we have a list of a list, and we don't want that list of a list? We just want it to be a straight up list. Well, we could either call flatten or cut to the chase and just use FlatMap. And that's what I want to do. Let's go back. So here, instead of map, I want to call FlatMap. Since this is creating a list of a list, I wish to flatten it. I'll go ahead and save this. Let's compile and run. There we go. Looks great. Now, each for comprehension can be filtered as well. Any object born from a class that contains map, FlatMap, filter, and ForEach can be used in a for comprehension. Now we'll find out a little bit later that we'll be using something called with filter, which is a little bit more performant, but its backup is called filter. We know what filter is, so let's try filtering out our for comprehension. We've had the result 6, but now what we'd like to do is a result 7. We're going to start off with a for comprehension. For I, this will start off with a list of 1, 2, 3, and 4. And we're going to put an if here. If I, whatever I is, and we'll say mod 2 is equal to 0, semicolon, because this is one statement. And as my second statement, this will be j, and its source will be a 5, 6, 7, 8 list. Finally, I will yield the tuple. I'll just print line that result. Let me bring this further up. There we go. Here's my result 7. Great. Now, let's compile and run. Now we have 2, 5, 2, 6, 2, 7, 2, 8, and 4, 5, 4, 6, 4, 7, and 4, 8. We only have the even numbers for I, and j enjoys all its elements being part of the final result. Let's go back. I was filtered, j was not. Now what I'm going to do here is put in a carriage return here, just so that everything fits nice and neat. Now, we could also do it to where j is constrained. So let's try that. For I, we'll just keep this as 1, 2, 3, 4. For j, on the other hand, let's make that a list of 5, 6, 7, and 8, except this time I want to constrain that to where j has to be less than 7. And with that, I will yield I and j. And if everything's in order, let's save, compile, and run. Great. Now we have 1, 5, 1, 6, then 2, 5, 2, 6, then 3, 5, 3, 6. In essence, j is now constrained to only 2 elements, just the 5 and the 6. Now, just so you know, there is no rule that the if clause for the filter needs to be on the same line as the assignment for the comprehension. In other words, this part right here. In fact, typically, you will find the if statement on a line onto itself. So let's create that. So this one I'll call result 9. And what I'm going to do with my result 9 is just bring the if statement in. Now, I think for those who are learning Scala for the first time, this can look rather confusing. That's why I opted not to show you that in the first place. I wanted to show you how the if statement's arranged and where the semicolons are. But you may see 4 comprehensions modeled like this for the most part. I'll call this one result 10 and save it. Now everything should be identical. Went ahead and saved it. Now let's go to the command line. Great. The last 2 match the previous 2. So to round things off, how about we take a look at what we've just done using FlatMap, map, and a filter combination, and rewrite those last 2 examples. Let's get started. Here, I will be rewriting result 9, and I'll call this one result 11. And result 11 is going to look like the following. Result 9 started out with a list 1, 2, 3, 4, except this time it had to filter each item. Then it had to do a flat map. Then for each item, we then brought in a list of 5, 6, 7, and 8. Then we'll provide a map, then bring in the j for each item, and then the tuple. Now we'll just print line result 11. Here it is, all in one big long line. List 1, 2, 3, 4. We'll filter each item, then we'll call flat map. For every item within the list of 1, 2, 3, 4, we are going to bring in another list, 5, 6, 7, 8. Then we will map each item. Here's the j coming in, and we will create a tuple for each one. And all the parentheses match. Let's save it, compile, and run. Looks good. Now let's rewrite the last one using a flat map, filter, and map. This is the one where the j is constrained. And we'll start off with a list of 1, 2, 3, 4, but the filter is not applied here. We will do a flat map. For every I, we will then take a list of 5, 6, 7, and 8, and this we will filter. What will we filter? Well, for every j, we need to make sure that j is less than 7, and then finally we're going to map each one. For every j, return the tuple. And we will print line result 12. And this right here, just for a note, we are rewriting result 10 using flat map and map and filter combinations. Now let's give it a try. Looks fantastic. Now we see they look alike. Problem is though, in the early days of Scala, filter was inefficient. That filter was causing a lot of great performance issues because of large collections being created every time. Because of that, there was something invented called with filter. It is a filter that is entirely lazy and will just prepare the subsequent map and flat map for their eventual calculation. Well, let's make our samples again, and by replacing filter with filter. Now I'm not going to type it again, I'm just going to go right in here and replace this filter with filter, and we will replace this one with filter. Again, this call is just going to be lazy and therefore efficient, where all the work is going to be done here in one fell swoop. Let's go ahead and save that, compile and run. Looks good and looks great. Now let's format it in the typical Scala way. You may have different ways of looking at it, but here's that one. I'm going to bring in FlatMap over here. Move that one down a bit. And here we are. Let's go ahead and save that, compile, and run. For comprehensions. Now, for comprehensions are just a map, flat map with filter, and for each behind the scenes. They look a lot like for loops, but they're not. For one, they could be assigned to a value. They return collections like sets, lists, options, etc. And any object that has a map, a flat map with filter, or a filter, and for each, they can be used inside of a for comprehension. In this session, we discuss fold left, fold right, reduce left, reduce right. This method, or these collections of methods, have implications to everyday functional programming, and we have to absolutely cover it. Let's start off with the following in a file called foldandreduce.scala. And our first victim, fold left. So let's go over to our file. Here's our file. Let's get started here. I'm going to create object, fold and reduce, extends app. Fantastic. We have that set up. Now let's take a look at the API for fold left. Okay, here we are at the API. We could do a range, list, set, map, whatever we want. And here's fold left. This is a parameterized type B. B is going to represent the total. A is going to represent whatever this list is. If we have a list of int, then A is going to be an int. B is going to be whatever we want to sum to, whatever the end result's going to be. This is a curried method parameter, two of them. First one is going to be the seed. Next one's going to be the function. And what we're going to return is a B, which is the end result. This is a reduction. Let's make this work. In our example, I want to create a result called fold left result. Let's do 1 to 10, and we're going to call fold left. And just as we saw in the API, we're going to start off with a seed. Next, we're going to create a function. This is a function that will take two ints. First one's the total, the running total that we're using as part of our reduction. And the next one is the next item. Let's print out the result. We'll save that. Now let's go over to the terminal. And we'll get 55. So this keeps a running total and processes each round with the next item. We start with 0 as the total. Let's go back to our code because that's the seed. And what we're looking at is this one right in here. Next one is our function. Total is going to have the running total. Next one's going to have the next item. What does fold left mean? It means we're starting from the left. In fact, we could change this around to do a print line to show us what the total value is and next value is for each iteration. Let's do that. Within here, I'd like to create a print line. And the print line states that for our total, let's print out the total here. For the next item, let's print out the next item here. And in fact, because we have two different lines here, we can no longer use a paren, we have to use a bracket. All right, same thing except we're just doing a print line with each iteration. Now, let's compile it and run it. We get to see here that we start off with a total of 0. Next item is 1. We're going to add those. We get 1 the next round. Next item is 2. We're going to add those. It's 3. Total is 3 for the next round. Next time, we have a 3, and we're going to take 3 and 3, 6. That's going to be the total for the next time around, and you get the drift. This makes it clearer for understanding. Now, there's also a reduce left, which does the same thing, except it will choose the leftmost element as the seed, and then proceeds with a fold. Again, the leftmost element is chosen automatically. Let's proceed with a reduce. This was our fold left, and what I'd like to do in this case, instead of fold left, I'd like to make this a reduce left. So reduce left does not require a seed, but we can keep everything else as is. Let's take a look to see what that does. Same thing, except this time we start off with a total of 1, chooses the leftmost element, and of course comes up with the same answer. Let's take a look at fold right. But first, let's take a look at the API for fold right. It looks nearly the same as fold left, so let's jump on over. Here we are. It looks nearly the same except for one thing, the function. For fold left, the function is total and next. The function for fold right is next and total. So we need to make sure that that is correct. What I'd like to do is create a fold right. This one, instead of fold left, let's call it fold right result. That looks good. Let's bring that over. We have some separation. Fold left, we'll call fold right. But what's different is the next item is coming first, total item is coming second. Looks good. Now let's take a look to see how this looks. We start off with a seed of 0, but the next item is 10. We're coming in from the right. Therefore, the total is 10. Next time around, we have 9. Therefore, we have 19, then 8, and so on. This is fold right. And obviously, we have a reduce right. Instead of reduce left, it's called reduce right. Call it reduce right. You make sure that it is the next one first, then the total. Let's make sure we have our name correct here. Okay, very good. Let's see what this ends up as. Looks really good. We take the rightmost element, 10, apply it to 9, get 19, and all the way down till we get 55. Now, all this was just an academic exercise to show you what fold and reduce does. But this could easily have been done with sum. And if you were interested in multiplication, that could have been done with product. Let's go ahead and save that, and let's take a look at the end result. There we go. Something should look eerily familiar about 1 to 10 dot product. I believe that's 10 factorial. A lot cleaner factorial than when we started working with recursion. Now, another thing worth noting, and let's just pick on the fold left first, is that for our fold left, we could have done a shorthand. Let's say for 1 to 10, fold left, start off with a seed of 0, and as far as our function, remember, it was total, then next. And that is a function, and what we were doing was total plus next. We could have done that, but the thing is, we could also do this. The first underscore is going to represent the total. Second underscore is going to represent the next. And all this is just a shorthand. So if we run it, we get 55. Now it's also worth noting one final thing. Let's go back to the code. That make string is essentially a reduction as well. And we've played around with make string already. Let's save that and let's give this a try. That's just a reduction, but it's a reduction onto a string. Nice little helper utility along with that. Fold left and fold right will perform a reduction operation with a seed value. Reduce left and reduce right will also perform a reduction operation, but without a seed. If it's reduce left, it'll choose the leftmost element. If it's reduce right, it'll choose the rightmost element. All your folds and reduces can be applied to lists, sets, maps, whatever type of collection. You could even use options if you'd like. And this concludes fold and reduce. This session describes zip. Zip is a method that takes two collections and intertwines them. Although it's hard to see how and when you would use them, all I could say is keep them in mind during your development. They certainly crop up at the right time and make your code really elegant. Here's how it works. Let's create a file called zip.scala and create two collections, then zip them up. Let's get started. Here's a file called zip.scala. It will be explicit this time around. 1, 2, 3, and 4, and val b will equal to list of 5, 6, 7, and 8. Now, what I'd like to do is zip between them. Now, this is a perfect scenario. Both of these lists have the same size. Let's check it out. Let's compile it and run it. We have the list of 1, 2, 3, 4, another list of 5, 6, 7, 8, and we called zip. This intertwines them. Now, let's try some other behavior. This time I want to see what happens when one side is larger than the other. Let's go back to our code. This time let's just use a range. We have 1, 2, 3, 4, 5, and we wish to zip with 6 to 9. 1, 2, 3, 4, 5, that's 5 elements. 6, 7, 8, 9, those are 4 elements. Let's see what the end result to this is. Remember, we had 1, 2, 3, 4, 5 on the left-hand side, but we only see 1, 2, 3, 4. Why? Because we're constrained by the right-hand side, which only had 6, 7, 8, and 9. Whatever could fit into it, that will be used. Now, what happens if the other side is shorter? So let's give that a try. In this case, let's say that we have 1 to 2, that's just 1 and 2, and on the other side we have 6, 7, 8, 9, so we have 4 items. Let's save that, and let's give this a try. We only have 2 items. You never know when zip is going to call itself out to you. Obviously, you see what happens here. And of course, you know that this is going to work for lists, sets, maps, streams, strings, etc. Zip intertwines two collections. The zip result will be the size of the shorter collection, either on the left-hand side or the right-hand side. And zip can be performed on various collections, could even be used on things like streams, strings, and options. And this concludes our very short session on zip. This one's called Finding Your Method and Function. I don't have anything scripted for this particular one. I am just going to take a look at the API and try a few things out. This is just to show you that there are a lot of methods on the API, and you can pick and choose different ones to take a look at their behavior and see if it works right for you. I'm going to do all this on the REPL, try a few things out, see what happens. So let's get started. Here I am at the REPL, and I'm going to choose a few of the methods that are available for a list. And we'll just pick on list. Let's go to the API. We have a wide assortment of different methods that we can use. Some of them we used, some of them we didn't. Here's reverse right here. We could just reverse the list if we need to. Shows all the different methods. There's scan. You can take a look at scan. I think you know just about how to read all the signatures. If you want to sort, this one allows you to sort by a function. Very interesting. Here's sum. There's tail. There's take. We didn't talk about take. We could give that a try. So we have a lot of different options that we can use. Here are all the two. So we can convert things to a seek, which is a higher abstraction for anything that's a list. We could do a toSet, to a stream, to a string. We have a lot of options at our disposal. Here's everything that we have with a list. Let's choose this one right here and take a look to see what this one does. This one partitions this traversable collection into two traversable collections according to a predicate. Oh, that's kind of interesting. So let's play around with that one. This one's called partition, and it looks like we give it a function that takes in an A and returns a Boolean. Well, let's have fun with that one. I'm just going to do this one on a REPL. We have 1, 2, 3, 4, 5, 6, and it seems we can call partition with a function. And this has to be a predicate, so how about we do odd numbers this time? I guess it wouldn't matter. This is a partition anyway. That's pretty cool. This creates a tuple. On the left-hand side are the elements that are odd, and on the right-hand side are the elements that are even. That's a really nice one. Let's try another one. And I just want to show you how easy it is to just take a look. I think you have all the information you need now. And let's choose this one right here. Here's group by. Group by will take a function. Now this is a list of A, so I'm assuming here this is a function that will take in an A and return a K of some sort, which it looks like is going to be a key. That's kind of an interesting one. So how about we do the following? Let's try a list of items. And how about this? Let's say we have a list of colors. Okay, so we have a list of colors. This is a list of string. Let's take a look at the API again. And this has group by, give it a function, and then give it whatever the key is going to be. This is called group by, and we're going to give it a function. This is the function. We're going to bring in the string, and we're going to get the head. And remember, head works perfectly fine with a string. We're going to get the head of each particular string on here. That's really neat. So we get a map where the keys are the characters. P has purple and pink, G has green and gray, R has red, and O has orange. That was a lot of fun. Let's take a look at some more. All right, let's scroll down a little bit and let's see what other good stuff we could find. We know what make string is. There's partition. We just tried that one. Let's try one down here and let's call take. Take is going to take a certain number of elements. This is actually a really popular one that's used often in functional programming. Let's do 1 to 100 and take 10. We just take the first 10. There's another one called, I believe, take right. Let's take a look. And here's take right. This one will take the last n elements, 91 down to 100. All you have to do is take a look at the API. Let's see, this one's interesting. Take while. This will accept a function, which is a predicate, anything that is a type A and a Boolean. And this one takes the longest prefix of elements that satisfy a predicate. Okay, fair enough. I think the way this one works is if we have, let's say 1 to 100, and we want to take while, this element is going to be less than 40. And there we go. So we're going to continually take information from there. Of course, we could have easily called take, but this is a predicate that we have here. So we're going to take while the number is less than 40. Okay, so we could just take a look more and more onto all the different kinds of things that are available. You have scan, you have reverse, you have reduce. We talked about reduce. We have non-empty, there's min, there's max, there's length, there's last. We have a lot of different things that we can work with. There's flatten, there's find. Oh, here's a nice one, distinct. That should be relatively easy. This works for a list. So if I have 4, 4, and let's say a 3 and a 2 and a 1, and call distinct on this, then we should just have 1, 2, 3, and 4. Again, look through, play with it. Use the REPL. REPL's a great way to play with whatever we need. And don't forget to also take a look at how you can create some of these things. Let me click on the object over here. And what I'd like to do is take a look at some of these. Oh, take a look at here. If I wanted to create an empty list, I could have just called, remember this is the companion object, list.empty. And I would have to declare a parameterized type for that. There we go. This creates an empty list of int. If I wanted to do a string, I could do that. If I wanted to create an empty list of a list of int, I could do that too. Also, let's take a look at some of the others. Now, again, I'm just picking on list. Take a look at set, take a look at map, whatever it is you want. Here's one called fill. Let's choose the simplest one. Produces a collection containing the results of some element computation any number of times. This will run, take a look at this. This is the by name parameter. We know what that is now, and we know what this is. List fill 10, and since it's a by name parameter, we can turn this into a block. Pretty neat. We know how all this works now. You have a lot of the information to get started with Scala, to use Scala, and to really enjoy Scala. Solving functionally with Scala. Now this one is free-flowing. We're going to use the REPL, and we're going to solve a problem functionally with Scala. We're going to take everything that we know, minus a few parts here and there that we don't, and come up with a solution. So let's get started. I'm going to head over to the REPL right now. Let's say we have a list of groceries. We have apples. We need to get milk. We need to get some delicious naan. We need some eggs. How about some oranges and almonds? And finally, let's get some peanut butter. Okay, so here we have our list of groceries. Apples, milk, naan, eggs, oranges, almonds, and peanut butter. What I would like to do is print this out as a list. Not only that, I want this printed out in a numeric list. So I want this to show 1.apples, 2.milk, 3.naan, 4.eggs, 5.oranges, etc. Not only that, I want these on a line of their own. So I want it to say 1.apples, carriage return, 2.milk, carriage return, 3.naan, carriage return, eggs, oranges, almonds, peanut butter. And I think we have most of the information. I think there's just one thing that you don't know at this point, but I think everything else you know. And here's the great thing about functional programming. We could take this one part at a time. Functional programming works really well for the brain. I even argue that if we learned functional programming instead of C++ or Java or C imperative type programming, then imperative programming is going to look weird to us. And I'll show you an example of what that means. I can think linearly. I see this list of groceries, and one of the first things I want to think about is I want to number them. Let's get started with that. So I have groceries, and I want to number each one. Remember, I want to say 1.apples, 2.milk, 3.naan, etc. So what I'm going to do is part by part, I'm going to choose zip with index. We know what zip is already. This is the intertwining of two collections. But what's the other collection? Well, I could do zip with 1 to 1000. That would do it. And we have the 1, the 2, the 3. That's one solution to it. Or we could do something else like groceries.zip with index, and we'll get something like this. Let's try the zip with index. Zip with index just means we're going to put the index of each individual element as a tuple on each one. Apples, the index is 0. Milk, the index is 1. Naan, the index is 2. Eggs, the index is 3. Great place to get started. Now, let's build off of this. So I have this zip with index, And now what I'd like to do is either flip these or add one to each element. How about we add one to each element? How are we going to do that? Well, with map. In fact, each item that's coming through here is a tuple. And what I'd like to do is keep that tuple around. I'd like to keep the first one, but for the second one, I'd like to add one to it. Again, just take it a bit at a time. What else would I like to do? Well, I have apples 1, milk 2, non 3, eggs 4. I'd like to flip those tuples around. I could do it here, but I could also do it here. I'm going to map each tuple, and I'm going to call swap. We learned this when we learned about tuples and tuple 2. Here we have a list: 1, apples, 2, milk, 3, non, 4, eggs, etc. Now, what do I want to do again? I'm looking at the elements, and I'm just proceeding one bit at a time. Let's do another map. And what I'd like to do with each tuple now is create a string out of it. I want to state the following. I want to get the first element, then have a period, and then do the second element. Close the string and close the paren. Now we're getting somewhere. We have a list: 1, period, space, apples, 2, period, space, milk, 3, period, space, non, 4, period, space, eggs, etc. I told you I wanted to make a string where each item in our grocery list is on its own line. And I think you already know the answer to this. We'll just do a make string, except this time our delimiter will be a new line. There it is. 1.apples, 2.milk, 3.non, 4.eggs, etc. Let's look at it again. Grocery, zip with index, map, map again, and then finally do a make string. We could probably refactor some of this. Like for this one, you just do underscore. That looks really nice. Now, one of the things that you could do is place in view. And what view is going to do is that it's not going to do any of these operations until you make a reduction. Remember when we talked about reduce and make string as being a reduction? Well, this is the reduction part right here. That's what a view will do. That will make the rest of this lazy, so we can put as many calculations as we want, and then we'll get whatever it is we need from it. Scala is really amazing with this. Also, one of the things that we could do is if we wanted to sort all these using the natural sorted order, groceries, view, sorted, zip with index, map, and then finally make string. How easy was that? All in one line. That's what you get with functional programming, the clean API. That's what you get with Scala. And this ends our video journey. I hope you enjoyed this video series in learning Scala. My name is Daniel Hinojosa. Thank you very much.